Shall we jump in?
Yep.
I guess I'm Ritchie Patterson. I'm the director of the Center for Bright Beams, and I want to start by welcoming everybody who has joined us from all sorts of time zones, all sorts of places, and I particularly want to welcome our speakers for today. I'm showing the program here. There's one change which is that Alex Romanenko from Fermilab will be speaking about SRF and colliders, and we're delighted to have him. It looks like an extremely exciting program, so I know we at the Center for Bright Beams are very, very excited about it. These days, the Symposium is a source of inspiration for the work that we do, as well as always being very, very interesting. To get us started, I thought I would give a little bit of an introduction to the Center for Bright Beams because I suspect that our speakers and some other visitors may not really know who we are, what we're doing. So here's just a taste. I'll start by asking why particle accelerators, and I suspect I'm preaching to the converted here, but nevertheless, it never hurts to remind ourselves how widespread and important particle accelerators are. They're used in industry for things like material sterilization, very important for semiconductor fabrication, both in the fabrication itself and in the quality control. In medicine, they of course produce medical isotopes and are also used in particle beam treatment for certain kinds of tumors that are in precarious locations. So in all, there are about 30,000 such accelerators in use today, and about 10 more are added each day. The number is growing very rapidly and promises to continue to grow as more capabilities become available. Of course, those of us in this room, and especially with today's topic, we think mostly of research accelerators, so the colliders for nuclear and particle physics that are today's topic, but also X-ray sources. And together, these are responsible for about 1/3 of Nobel Prizes in both physics and chemistry. At CBB, Center for Bright Beams, when we think about particle accelerators, we also include electron microscopes, which in reality are particle accelerators in miniature. And then, of course, the impact is even broader. So the Center for Bright Beams was established by it's a National Science Foundation, Science and Technology Center, whose vision is to revolutionize the brightness of beams available to science, medicine, and industry. And in the cartoon on the right, I explain, at least heuristically, what we mean by brightness. It's the top bunch is a sort of a diagram of a bunch of electrons traveling to the right with each little arrow representing the momentum of an electron. That's a low brightness bunch. The electrons are diffuse, they're going every which way, and we're trying to transform that bunch into the one at the bottom. It's a high brightness bunch. So our intent is to transform the reach of electron beams by introducing new methods that increase the brightness that's available and reduce the cost and size of accelerators, because those are indeed often driving factors as well. We're not building all of these accelerators, so we need to transfer whatever methods we develop to national labs and industry. And then very importantly, we're preparing a diverse group of students and postdocs for leadership in accelerator physics and other fields. And I will just remind ourselves something that we're keenly aware of in the United States, which is that the annual demand for new PhDs in accelerator science is about 3 or 4 times the number that is actually produced by US universities today. CBB is a collaboration of a large number of universities and national labs. I'm showing them at the bottom. And we are always growing. We have divided our research program into 3 different research themes. At the top here is a little cartoon of a particle accelerator, starting from the source on the left, where we think about photoemission sources of electrons. The beam then travels from the source through an accelerating field and on to a target. And so CBB also addresses this acceleration stage through superconducting RF cavities, and also the transport of the beam itself, which is absolutely crucial to having high performance at your target, whether that's a collision point or a material sample. So we have these three areas: beam production, which is methods for better photocathodes, beam dynamics and control, and beam acceleration. And in each of these cases, our intent is to gain new fundamental understanding in order to transform the methods and so on that give you the brightness that is needed for science, medicine, and industry. And of course, the impact of brighter beams can be enormous. So we think of things like electron microscopy and ultra-fast electron diffraction with online tuning and very short pulses, and that would allow imaging at the atomic scale with new spatial and time resolution. We think of the topic for today, which is colliders with higher luminosity and cheaper acceleration, so that we can get new insights into protons through something like an electron ion collider that we'll hear about, or into the moments of the Big Bang from a high energy electron-positron collider or proton collider. And we'll hear about those too. CBB also thinks about X-ray FELs with brighter electron beams that can lower cost or give you a higher energy reach with the X-rays, and also compact X-ray sources. And then finally, new turnkey superconducting RF-based accelerators, but with vastly simpler refrigeration systems than is required today. And that would make that technology available, for example, to industry for new green technologies and to scientific labs, but now in commonplace in university labs. So I want to say just a little bit about each of our themes. One of them is new photo emission sources. And of course, that happens where you shine a laser pulse onto a photocathode and out comes an electron beam. We are trying to make an electron beam that goes completely forward. In other words, the transverse momentum of those electrons is small. And we'd also like to make very dense bunches. So on the right-hand side, you can see this scale here. This is transverse momentum, small is good. Typical cathodes operating in the world today are up here between 100 and 1,000 on this scale. Already, what CBB has done is identify the sources of transverse momentum in photocathodes. And by then putting all that knowledge together, last year we were able to make a photocathode that achieved transverse momentum squared down here, which is about 2 orders of improvement over what's in typical use. Now that, first of all, was a collaborative effort. I always want to remember our collaborators. It was also at low current density. And what we have understood is that you really need a different kind of cathode if you want to achieve similar transverse momentum squared, but at high current density. And so that's what we're working on now. And we believe that we can get to somewhere in this range or even better using semiconductor photocathodes. And then you have to do something, capping or something, in order to preserve their robustness, because otherwise they're very delicate beasts. We need them to survive in real accelerators. So all of these achievements depended on lots of advances in understanding these many effects that drive photo emission. And you can hear much more about this at the poster session. We look at brightness preservation. This is a scale of emittance going from 1,000 nanometer irradians up here over many, many orders of magnitude down to the Heisenberg limit. Emittance is just the delta X, delta P of the beam, and small is good. But, so here is the nominal emittance expected for LCLS2, X-ray free electron laser under construction at SLAC. and that last year we showed that you could optimize it and achieve and use a CBB photocathode to get maybe an order of magnitude improvement in principle. We are also very close to demonstrating an emittance of around 1 nanometer radian in an UED beamline. That, of course, has much lower bunch charge than they need for an X-ray free electron laser. And we've shown that you can even go a little further if you optimize more. You need to be able to measure these tiny emittances, and so we've developed knife edge diagnostics with the needed resolution. And interestingly, we've measured the emittance in an electron microscope. And maybe the exciting thing here is that it turns out that emittance is a wonderful figure of merit for electron microscopes. And by optimizing that and applying CVB technology, we think we can improve performance there. So there's an enormous range here, all with important applications. In beam dynamics and control, we have several focus areas. One is to conserve. That's what I just showed you. How do you preserve terrific brightness coming from a photo injector all the way down to your target? We also want to cool the beams. And we'll hear much more about that in the talks today. CBB is focusing in particular on optical stochastic cooling. And then finally, there's control. How do you control the phase space? And here, what CVB would like to do is explore machine learning methods and other techniques, but also understand what their limitations are, where they're applicable, where you can gain, and where they're simply not really helpful. So we hope to get that kind of fundamental understanding over the next few years. We'll also talk about just a little bit about what we're doing in superconducting acceleration. CVB has put a lot of its effort into understanding niobium-310. This diagram up here in the upper left is a superconducting RF cavity, and Alex Romanenko will tell us much, much more about them later today. But they're the gold standard for beam acceleration today, and they're made out of niobium. And the idea is that you can coat the interior of the niobium with tin to make niobium-310 and get better performance. And what CVB has worked on is improving the quality of that coating. And that's led to good gradients and about 70% less power consumption than you would have with a niobium cavity operating in the same performance regime. And so here is a scale showing cryogenic cooling power. Typical niobium cavities operate up here. A cavity using CVB growth methods has operated with about a factor of 3 improvement. And we think that we can go down another factor of 3 and increase the gradient. And all of this has required understanding quite a lot about the niobium-310 and its growth and its defects and all of that. To translate this cooling power scale into something concrete, here's a picture of the cooling systems required. On the left is the cooling system required for a niobium standard traditional high performance niobium cavity. But if you can do this niobium, well, since we can do this niobium-310, we can cool a similarly performing cavity with a much, much simpler system. Here's just a little hint of the work that has led to these kinds of the advances. We've done a lot of work on understanding the impact of the tin stoichiometry, the tin concentration in the niobium-310 coating. You'd like this orange. This is level. Sometimes you get holes. That adds a second band gap, which increases the surface resistance. And understanding the growth processes has allowed us to suppress this kind of defect. We have also been studying grain boundaries. We have found that tin tends to aggregate in the grain boundaries. That reduces the density of states at the Fermi level and lowers TC. And we also see that vortices tend to enter at grain boundaries, and that's a potential source of heating and quench. So we've been pulling together all kinds of different disciplines to understand these effects. Finally, on nitrogen doping, here's some beautiful, beautiful images of niobium that have shown that doping suppresses nanohydride formation. And then we've coupled that with density functional theory calculations that explain the mechanism for that, namely that with the doping, the hydrogen tends to sit at different sites that's not conducive to the nanohydride formation. So that's just a little bit of the flavor. Here's how we work. We tend to get lots of people with lots of different expertise all into the same room often, and as we work our way through understanding these processes, it's a really exciting process. And here's at least one of the directions we're going in the future, which is superconducting RF surfaces by design. And this is just one example. Really, all aspects of CBB work on this same model of intensive collaboration. Here are our grad students and postdocs. And I have to confess for some of our students and postdocs that this image is a little dated and I might not have everybody, but it's a fabulous team and does very impressive work. And of course, these are training in a very high demand field. I mentioned knowledge transfer early on. We have a number of industrial partners who are collaborating with us on all sorts of different aspects of the work that we're doing. And we also are collaborating a lot with national labs, and here are just some examples. And one of the things I like about this is that you can see that we're collaborating with multiple labs in multiple different ways. And that makes us, it makes us effective and focused, and of course improves the research. So just to summarize, we are the NSF Center for Bright Beams, and have certain focus areas. We're very eager for close collaboration with labs and industry for better, faster progress, and so that our methods can be integrated into future accelerators, like the ones we're going to hear about today. And we train students and postdocs in accelerator science, and importantly, they get hands-on experience. So I will stop there, and if there are questions, I can take them. And if not, we can simply move on and hear from, and jump into the rest of the program.
Yeah, that sounds good, Ritchie. Maybe especially those our guests, if they have any questions, this is a unique moment about CBB or anything.
Actually, it's not quite a unique moment because there will be the poster blitz and poster section later on.
Yeah,
and that's
I meant that overall about CBB, specifically to our director. That's what I meant. Later on, it's more for our students. Yeah, thank you for clarification, Ritchie. Sounds like everybody is eager to listen.
I think that's absolutely right, and that's great. So I'm gonna stop my share, and I believe Frank is next up.
That's right. So let me introduce Frank. First of all, I'm Youngki Kim from University of Chicago. I'm a member of CBB, working on theme 3, the dynamics and control area. So today we have a very exciting program, as Rich mentioned earlier. In particular, we will look at all different aspects of a future particle colliders. So first speaker will be Frank Zimmermann. Frank is a senior accelerator scientist at CERN and the deputy leader of the Future Circular Collider called FCC study. He also serves as the lead editor of the journal Physical Review Accelerators and Beams. Before joining CERN, Frank has worked at SLAC and DAISY in Germany. Frank has many honors and recognitions, including the European Physical Society's Accelerator Prize in 2002, and the US Particle Accelerator School Prize in 2019 for achievement in accelerator physics and technology. Frank is a fellow of American Physical Society and presently the vice chair of the APS Division of Physics of Beams, DPB. What that means, he will chair the DPB in 2022. Frank, together with Michiko Minty, who is the next speaker, wrote a book called Measurement and Control of Charged Particle Beams. Please join me in welcoming Frank, who will present Collider Overview. Frank? Can you hear me? Anybody?
I can hear you.
Sorry, Yankee. Sorry. My microphone was off. Sorry. Thank you very much, Yankee.
Okay.
I have a special microphone I borrowed from my daughter. She is in a rock band. I have special buttons here that I need to push. Yeah, thank you very much for the kind introduction to you and for the invitation to you and Ritchie. It's a pleasure and privilege to talk at the symposium of the Center for Bright Beams. And I like to share my slides with you. If I manage, let me see. Share the screen. Yes, this. I don't know. Is it working? Yes.
Yes.
Okay. So Yankee invited me to give an overview of future colliders. I worked on colliders for more than 30 years, and now I have to condense all my knowledge into 20 minutes. It's a rather impossible task. So I picked a few topics that I find interesting and exciting. Okay, I put here in the background a few candidate sites for future large colliders. Why do we need colliders in the first place? Colliders were kind of invented in the 1940s and patented in the 50s. And the main idea is that if you hit, until the advent of colliders, there were only fixed target experiments. And if a beam is excited and sent against a fixed target, then the center of mass energy in collisions between beam particles and constituents of the target goes with the square root of the beam energy and of the mass of the target particles. So it's not extremely efficient use of the beam energy. So the collider idea is to send two particles in the opposite direction and crash them against each other. And then the center of mass energy is directly proportional to the beam energy. It's actually 2 times the beam energy. So this is a big advantage compared to fixed target experiments. Nowadays, there are also some colliders which have sent again in collision beams of different energies, and then the formula is slightly different, but you still have a big advantage compared to fixed target experiments. This shows you the history of collider energies over the past 60 years. Not all the colliders are shown, but the most prominent ones, starting in the 60s with Princeton, Stanford, Web2, and Ardone in the three different regions of the world. And then actually in blue is shown the electron-positron colliders. This is, the vertical scale is logarithmic, the center of mass collision energy. And you can see that these E plus E minus electron-positron colliders, they increased in their energy by about a factor 200 since the days of the Princeton-Stanford experiments. The record is held by Lab 2. There's also SLC, Tristan, etc. Then you have another curve here, which are the red squares. These are the hadron colliders. There were not so many. There were only 5 of them, actually. The first one was ISR proton-proton collider at CERN. Then there were 2 colliders colliding protons and antiprotons, the SPP by S and the Tevatron. And then there is RHIC and the LHC, both colliding protons against protons. And RHIC and LHC also both have a heavy ion program, which is shown here underneath. There was one electron-proton lepton-hadron collider, HERA, at DESY, which is where I started my career. So the progress in center of mass energy was made on the one hand by making bigger machines, and on the other hand by introducing new technologies. And already mentioned by Ritchie, superconducting RF systems played a major role in pushing the energy, in particular for the E plus E minus colliders. Petra was one of the first machines with large SRF installation. Tristan had the full large scale SRF, and then Lab 2 would not have been possible without superconducting RF. On the Hadron Collider side, there was a big jump from the SPP by S to the Tevatron, the machines with similar circumference, and this was made possible by introducing superconducting accelerator magnets. And then there are two machines, actually LHC and Hera, which use both superconducting RF and superconducting magnets. So advances were made in the energy scale were made mainly by introducing new technologies and new materials. Let's look a little bit. I have this nice slide borrowed from Amalia Ballerina, which shows the discoveries. Actually, the present standard model of the particles and forces, the heavy elements of the standard model were all discovered at colliders. Spear co-discovered the charm quark and they discovered the tau lepton. Petra discovered the gluon, the SPP by S, the Z and W bosons, Tevatron the top, and the LHC discovered the Higgs. So you can see that all the fermions of the standard model were discovered in the United States, and all the bosons and integer spin particles were and carrier force guys were discovered in Europe. So colliders have a proven track record as instruments, precision instruments for instruments for discovery and for precision measurements. There are still many people ask, why do we need to continue? We have discovered all these particles. The standard model is complete. Why do we not stop now? I'm asked again and again. So there are still many open questions. The known matter makes up less than 5% of the known universe. We know there should be a large portion of dark matter, which is more than 5 times the amount of the known matter. And perhaps there's also dark energy. Despite of several B factors, we still do not know why there is more matter than antimatter in the universe, and we have no theory, I believe, which links gravity and quantum mechanics. So there is no sign at the LHC so far. There has been no sign of supersymmetry. So we have at the moment perhaps no real answer to how to combine these two leading centuries of the past century. Theories, yes. Anyway, for the heavy ion collisions, there are other questions like QCD, quark gluon plasma, the proton spin puzzle, etc. Maybe Michiko will talk about those in the next talk. I already told you about the energy. There's a second figure of merit in colliders, which is the luminosity. And this is important because the event rate is given by the cross-section for a physics process times the luminosity. And the cross-section is given by the physics process, and we cannot do much about. If we don't want to wait centuries to find a new particle, we must have enough luminosity, and the luminosity is given by parameters of our collider, of our accelerator. So this normally we don't have a continuous beam flow of particles, but we have small packages called bunches, and the number of particles, for example, electrons or positrons or protons in a bunch goes in as a square in this luminosity formula. And then it goes with the inverse cross-section of the beam at the collision point. So we want a small beam, we want a high charge in each colliding bunch, and then there is a collision rate of bunches. So we like to have many bunches colliding per second. That means normally a lot of bunches with a close bunch spacing. There's also a geometric factor, but typically that doesn't change. That's within a factor of 2 or so. The problem is that the cross-section tends to decrease as 1 over energy square. That means as we go up in energy, we need to increase the luminosity, and dramatically so. And this has actually been accomplished, as you can see here, over at least the last 60 years. As the energy increased by a factor of a few hundred or 1,000, the luminosity increased by more than 6 orders of magnitude from the CBX to the LHC and KEKB. So far, we have well kept up with the required luminosity values by making better and better accelerators and more powerful colliders. The present flagship collider is the Large Hadron Collider, the LHC at CERN. You may have heard about it. It has a circumference of almost 27 kilometers. It accommodates 2 counter-propagating proton beams, here shown in red and blue, which intersect and cross each other at 4 collision points. And these collision points are the locations of 4 experiments. So the 2 high luminosity experiments, CMS and Atlas, which are here diametrically opposed. And then 2 special purpose experiments, ALICE and LHCb, mostly for heavy ion physics and flavor physics. So this is the world's highest energy hadron collider in operation. Peak luminosities so far were up to 2.2 × 10⁻³ inverse centimeters per second. And this is a bit too much for the experiments to handle. So actually luminosity is leveled to a value of about 1.5 10 to the 34 in order to keep the number of separate events during one bunch crossing limited to a value where the experiment has enough resolution to resolve. Typically, there are several tens of events at the same time during a bunch crossing. Total integrated luminosity so far is about 200 inverse femtobarn, and you can see the progress over the different years of running. It has been running extremely well. Right now, we are in the middle of a shutdown, which probably due to the pandemic will last a bit longer than initially foreseen because CERN has been a bit locked down over the last couple of months. I'm back in my office today, actually. It's the fifth time that I'm back in my office. Near future colliders, there are a few which we know will come. We are pretty sure there's a high luminosity LHC, which is an ongoing upgrade of the existing Large Hadron Collider. The goal is to to upgrade the machine and the detectors and to operate in the future at a level luminosity of 5 10 to the 34, perhaps 7.5 10 to the 34. And the goal is to accumulate 3 inverse Autobahn. I remind you, at the moment, we have about 0.2 inverse Autobahn. So by the end of the 2030s, we should have more than 10 times more integrated luminosity. This is the overall schedule. There are a few long shutdowns, which last 1 or 2 years each. At the moment, we are in this long shutdown too, where we have a major upgrade of the injector complex. A new LINAC is connected, and we have ejector chain consists of a LINAC, a PS booster, the old proton synchrotron PS, and then the the SPS, and then from the SPS we inject into the LHC. So at the moment, we are connecting the LINAC 4 to the PS booster, and the energy of the PS booster is also increased. And the new LINAC is an H- LINAC instead of a primarily a proton LINAC. So anyway, this is an irreversible upgrade of the injector complex, which should double the beam brightness. So that will please you because you are Center for Bright Beams. We are trying to make the beams brighter by a factor 2 after this year. And then in the middle of the 2020s, there will be a major upgrade of the collider itself. We will replace the interaction regions around the main experiments, and also the experiments themselves will be upgraded so that they can deal with a higher level of pileup. And then this program will continue probably around 2038 or 2039. 2 other colliders worth mentioning is the electron ion collider, was approved earlier this year by the DOE. If it goes ahead, it will be built at Brookhaven in a collaboration with JLab, and it will start operation around 2030. It will collide protons and electrons with energies from 30 to 140 GeV and luminosities which are close to the luminosity of the LHC. Another machine which has been already built is a Super KEKB. It's in the same tunnel and uses some of the components of this former KEKB factory. It is presently being commissioned. It runs at the center of mass energy of 11 GeV, so-called Upsilon resonance, Upsilon 4S resonance. And target ultimate design luminosity 8 10 to the 35, which is a factor 40 or so above the luminosity of the previous peak factor. We just had a review. At the moment, they have a luminosity record at 2.4 10 to the 34, so there is still a rather long way, more than a factor 10 to go to reach their target, and they hope to accumulate around 50 inverse Autobahn in the early 2030s. They have achieved a vertical beta star of 0.8 millimeter, which is a world record, and the vertical beam size at the collision point is close to 200 nanometer, which is much smaller than at the former linear collider SLC. Let me remind you that there are several basic types of accelerators. There's a linear accelerator, which we have also at CERN in our injector chain, which mostly consists of a series of radio frequency cavities. The beam goes through in a straight line and is accelerated and gains energy. Then we have circular accelerators, synchrotrons to accelerate, or storage rings to store the beam at a constant energy. In synchrotrons, we have fewer radio frequency cavities, but the beam comes back again and again, and it can increase its energy on successive passes through this cavity. So the most of the past high energy colliders were based on this concept. There's a hybrid scheme, in particular also being developed at Cornell, which is a so-called recirculating energy recovery LINAC, where you have a long LINAC, but then you recirculate and you go several times in a circle through this long LINAC, which has some advantages because overall you do much fewer turns and you can have a much smaller emittance, and ultimately you can also decelerate after you have used the beam and recover the energy of the beam. Okay, so now I go a little bit into detail for circular and linear colliders. The circular machine, all the hadron colliders so far have been circular machines, and there is no reason to believe in the near future that anybody would want to build a hadron collider which is not circular, because to go to 100 TeV energies with a linear machine, you would need an enormous length. Also, almost all E+ E- colliders so far, with one exception, have been circular. The one exception was the SLC at Stanford. In a circular machine, the particles collide many times. You can have multiple collision points. One disadvantage is the electrons and positrons, they lose energy due to synchrotron radiation, and the energy loss per turn goes with the energy to the force power divided by the bending radius. So one reason to go to bigger machines is that we reduce the synchrotron radiation, but energy scaling with the force power is quite strong. So at some point one reaches a limit. And that is the reason why straight Linacs were proposed for future colliders, where you collide electrons and positrons in a straight section and you bring them into collision. In these machines, there is negligible synchrotron radiation during the acceleration, but you have only one collision per particle. Instead of colliding particles over and over again, you have only one chance to collide, and then you throw away the beam, at least in the present designs. You need a very large accelerating system, and you need, in order to compete, because of this feature that you have only a single collision, in order to compete in luminosity with circular machines, you need a very small spot size. And this small spot size results in very strong fields during the collision, which gives rise to a different type of synchrotron radiation, which is called the Beamstrahlung, which only happens during the collision process. Now, let me first go now to the future hadron colliders. At the moment, two future 100-kilometer hadron colliders are proposed. One is the FCC-HH based at CERN, and the other is a superconducting proton or a super-proton-proton collider based in China. They have somewhat similar parameters, already the same circumference. By the way, this shows you the history of hadron colliders in a double logarithmic scale, peak luminosity versus center of mass energy. You have the tevatron, you have LHC, and you see the next step from the LHC to the FCCHH or SPPCC will be similar to the step, both in energy and luminosity will be similar to the step that was made from the tevatron to the LHC. So which is about in order of magnitude in both parameters. The goal for FCCHH is to collect at least 20 inverse Autobahn per experiment, which is to be compared with 3 inverse Autobahn for the LHC. And the energy of these machines is given by the bending radius times the magnetic field. So in order to make an order of magnitude progress, we try to push the magnetic field as much as possible, and the rest, actually most of the gain comes from making a larger machine. Going from 27 kilometer to 100 kilometer is about 4 times larger. So we gain a factor 4 here, and the magnetic field, we can hope to make a factor 2 larger. By the way, tevatron had a introduced niobium titanium magnets with a field of 4.2 Tesla. This niobium titanium technology was pushed, and LHC uses 8.3 Tesla niobium titanium magnets, which is about the limit. You cannot go much higher because the magnet will will no longer be superconducting if you push beyond 9 Tesla or so. If you want to go to higher energy and higher field, you need a different superconductor. And the main candidate at the moment being developed at CERN is niobium-3 tin. The high luminosity LHC will use more than 20 magnets based on niobium-3 tin with a field of about 11 to 12 Tesla at the coil. So there will be 16 new final focus quadrupoles with 12 Tesla peak field, and there will be a couple of 11 Tesla dipoles installed for the high luminosity LHC. This is a big step in technology from the LHC, but the goal for the future colliders would be to have thousands of magnets with 16 Tesla. So the good news is only last week, Fermilab colleagues, they managed to demonstrate 14.5 Tesla in an niobium-3 tin demonstrator dipole. This was announced in the Fermi news just early last week. So there is progress, and this shows in principle we can build niobium-3 tin magnets which are close to the 16 Tesla field that we desire. But to build thousands of such magnets reliably and for an acceptable price, there's still a long way. There's still a long way to go, I think. several tens of years probably. Anyway, now I come to the future E plus E minus collider proposals. There are at the moment 4 candidates. There's the International Linear Collider proposed by the high energy physicist in Japan. In the baseline, in the initial stage, it has a 20-kilometer length and a center of mass energy of 250 GeV, which covers the Higgs production. It can be extended later to 30 kilometer with a 500 GeV center of mass energy. It uses 1.3 gigahertz bulk niobium cavities with a gradient somewhat above 30 megavolt per meter, 31.5 or so. There's another linear collider proposed at CERN, which uses warm copper radio frequency systems with a higher gradient, up to 100 megavolt per meter at 12 gigahertz S-band. It uses a new technology, so-called two-beam technology, to distribute the energy along the linac and to drive the main beam. There is a so-called drive beam portions which are sent along the accelerator to carry the energy to the places where they are needed to accelerate the main beam. There are 2 circular collider proposals which are very similar to each other, both 100 kilometer long. One is the FCCEE, which should operate between the Z pole at 91 GeV center of mass up to 365 GeV, the TT bar threshold. It uses mostly 400 megahertz superconducting F, not bulk niobium, but niobium on copper. And for the final stage TT bar with much fewer bunches, it will use additional 800 megahertz cavities. And the other candidate is the CEPC, same circumference, similar layout. The only noticeable, this is to be built in China. They have something like 6-7 different candidate sites already studied. The only difference is they don't want to go to the TT bar. They only run from 90 GeV to 240 GeV. They have only 3 energy modes of operation, and they want to use 650 megahertz RF system. Okay, this is a very brief slide. Do I have time? Yes, hopefully. Yes. Anyway, just to illustrate once again the point, in a linear collider, you accelerate and then you dump the beam. You must fill the RF structure and then you transfer the energy to the beam. And the RF on each shot must supply the full beam energy for each collision. While in a circular machine, the RF only needs to compensate the synchronization loss per turn. It's a CW and it's quite efficient, almost 100%. With almost 100% efficiency, RF is transferred to the beam. And at the lower energy modes of operation in FCC and CEPC, about 1 per mil of the energy is lost per turn. That means one needs to provide 1 per mil of the beam energy per passage. At the TT bar, it's about 1%, so slightly above 1%. So that means there's a factor of 100 or from 100 to 1,000 difference in the efficiency, in the energy needed per collision. So this has to be compensated with very small spot sizes at the collision point in the case of the linear colliders. Anyway, this plot was in the briefing booklet of the European strategy, which shows the efficiency of the future colliders in luminosity per wall plug power on a logarithmic scale as a function of the center of mass energy logarithmic. And you see the main features is that the circular machines are extremely efficient at low energy to study the Z and W boson, the Higgs up to the TT bar. They seem to be a very efficient solution. Actually, this FCC can produce 100,000 times more luminosity than lepted using the several new ingredients that were demonstrated at the SLAC and KKB factories at Daphne and at Super KKB. And then you have a regime where the linear colliders excel, maybe from 350, 400 GeV up to a few TeV. And then there is a ILC and CLIC do very well, and they don't have this sharp fall of luminosity with energy, but actually they increase even luminosity with energy slightly towards high energy. At very high energies, it's predicted that the circular muon colliders will be the most efficient technology. So starting, I think this is rather speculative, but you make an initial investment in the muon production complex, which is very expensive. And then the more you accelerate, the acceleration is comparatively cheap compared to the production and cooling. And the higher in energy you go, the more efficient the muon collider appears to become. So for above 3 TeV, projection is that the muon collider will be the most efficient machine. Okay, now a few words about synchrotron radiation. In circular machines, you bend the beam, and whenever the beam is bent, there is synchrotron radiation energy loss. And over one full turn, 360 degrees, the energy loss goes with the gamma of the particle to the force power and 1 over the bending radius. And the total synchronization power is given by the beam current times this energy loss per turn. So to give you some examples, for lab, in the final stage of lab, there was about 23 megawatt of synchronous radiation emitted at lab 2 in the search for the Higgs. For the FCCEE, we put a design constraint arbitrarily as 100 megawatt, which gives the same power per unit length as in lab. Actually, FCCE has 2 different chambers, so per chamber is actually almost half the power emitted that we had in lab. But it's a substantial, so this RF system needs electrical input power of the order of 160 megawatt in order to provide 100 megawatt radio frequency power to the beam. The protons also becomes important for the protons. In the LHC, we have 10 kilowatt of proton synchronous radiation, which looks negligible, but this increases to 5 megawatt for FCCHH. This looks small compared to 100 megawatt, but this is emitted inside the cold magnets, and it's quite challenging and expensive to remove this heat from inside the cold magnets. We have a beam screen inside, which should shield the magnet at a somewhat higher temperature. The beam screen temperature for FCCHH optimized at 50 Kelvin, but to extract this 5 megawatt at 50 Kelvin needs more than 100 megawatt of electric power for the cryo plant. So the synchronous radiation puts a similar challenge also, maybe even more difficult challenge for the future hadron beams. Linear colliders don't have this problem, but they have this Beamstrahlung problem. This is illustrated here. This is the luminosity spectrum on a logarithmic scale for click. At 380 GeV, you have this blue curve, and you find that about 60% of the total luminosity is within 1% of the target energy. But this at 3 TeV, this drops to 33%. You have a very wide distribution in your luminosity spectrum going down here. Okay, it's a small level, but it goes down to 10% of the target energy. So the energy is widely smeared out. This might affect energy precision of the E plus E minus class. On the other hand, maybe it also helps in looking for new particles, because you don't need to hit a resonance precisely to produce a new particle. But overall luminosity, effective luminosity will be lower due to this Beamstrahlung spreading. Okay, one slide on the muon collider. Since the muon is 200 times heavier also than the electron, the synchronization is about 10 to the 9 times less, and there is no Beamstrahlung problem in the collision. There are 2 production schemes proposed. The one is a kind of traditional scheme that was worked out in great detail by the US MAP program in 2015. It's proton driven. Protons hit a target, high intensity proton beams hit a target, produce pions which decay into muons. With a large emittance, these need to be cooled and then rapidly accelerated and collided. A few years ago, our Italian colleagues, Pantaleo, Raimondi, and others proposed a scheme based on positron annihilation. You need 45 GeV positrons hitting a fixed target to annihilate with electrons at rest, and then you get 20 GeV muons with a very low emittance, just above the production threshold. The cross-section is very low, so you need a very powerful positron beam in a storage ring, and you may need to cool also these positrons again and again. But the muons that are produced have a very small emittance. You don't need the ionization cooling, and you can quickly accelerate. And with a small emittance, you can, with fewer muons, with a lower emittance, you can get a high luminosity on paper. The muons has one problem, is that they decay within a few hundred or maximum a few thousand of turns. So that means we need to very rapidly accelerate them, and the higher energy we want to reach, the more difficult this acceleration. Perhaps plasma acceleration, which is very high gradient, could be an option for the muon collider, because we don't, maybe the muon emittance is relatively large compared to emittance in electron beams. Perhaps plasma could be ideal for a rapid acceleration of muons. Another problem is that this decay of muons produces neutrinos, and the cross-section of neutrinos interacting with matter increases linearly with energy. Plus, due to the Lorentz bus, the flux of the neutrinos also increases with energy square. So you have a huge increase of potential radiation with energy that was discovered by Bruce King and others in the late 1990s. This is a drawing from Bruce. So if these neutrinos hit some matter, then they produce a shower, and the person standing nearby will be irradiated. So At the moment, there is, I believe, no solution for muon colliders beyond 10 TeV due to this radiation problem. Now, energy consumption is a big concern for society.
Frank,
Anyway,
would you be able to wrap it up?
yes, I try. I just show you. Okay, I have a few ideas for the future, so I want to go quickly. Anyway, energy consumption. You see here the history of Lab 2, LHC, HLSC, typically 1 terawatt-hour at CERN for every year, and this is also projected for the future FCC machines. We will not increase this by more than a few tenths of %. How can we make further boost collider energy efficiency? There are 3 paths: more energy efficient technologies, multiple collision points, or energy recovery. This shows you progress in SRF, already mentioned by Ritchie. Over 30 years, a tremendous progress using nitrogen doping, nitrogen diffusion recently, and other technologies. So the heat load and losses in the cavities are greatly reduced. They are characterized by this Q unloaded Q value, and the gradients have greatly increased. And there is hope to also improve the gradients even further to 100 megavolt per meter or more in superconducting RF. RF power sources were invented. The Kleistron is the old source. It was invented 80 years ago and developed during World War II for radar technology. In recent years, there is a new revolution in the Kleistron efficiency. There is this worldwide collaboration, and there are 3 new concepts to improve Kleistron efficiency, and one can hope to gain a factor of 20% or so. After 80, for an 80-year-old technology, this is a remarkable progress. And so there have been already several prototypes built, and it seems that the new simulations and ideas are working. So going from 60 to 80% Kleistron efficiency can save tens of megawatt power for the future colliders. Also making more efficient magnets is important. We have twin magnets for the FCC, where we have a common coil for electrons and positrons, and the magnets are very simple: 2 bus bars on both sides of the beam pipe, and then two metal plates put on top and the bottom. This can be assembled in the tunnel. It's very cheap and doesn't need much power. And the Chinese have actually adopted a design which is almost identical. Multiple collision point for circular colliders is rather obvious. The FCC, EE, and CEPC have 2 collision points. We are studying the possibility to do 4 collision points. We need to preserve the superperiodicity to avoid harmful resonances and to maintain a good beam-beam performance. Also, by the way, linear colliders could also in principle use multiple collision points. There was one future linear collider approved. The only one ever approved and under construction was VLAB in Prodvino. Unfortunately, it was stopped when the Soviet Union collapsed. But this VLAB design, among other things, had the positron source, which later became the Tesla and ILC positron source, undulator base. But it also had multiple collision points, as you can see here. VLAB had actually collided the beams 5 times, and this multiplied the effective luminosity by a factor of 5. That could be an idea for future machines. Another idea is energy recovery. Maury Tigner is well known. He proposed linear colliders in 1965. And in this paper, he only considered linear colliders based on energy recovery. You accelerate, you collide, and you decelerate and recover the energy. 11 years after Maury, Ugo Amaldi and others at CERN, they proposed a 300 GeV E plus E minus collider. Looks very similar to the ILC superconducting, but it was also based on energy recovery. You accelerate, you collide, you decelerate, and recover the energy. So why not also today? Here are 2 ideas. Now we can learn from the light sources. Here is a proposal for the XFEL in Hamburg to upgrade it to CW and energy recovery mode of operation. You need to introduce chicanes, maybe to separate accelerating and decelerating bunches to avoid parasitic collisions. Another possibility is to use a dual axis LINAC as developed in the UK, where you could decelerate one beam in one LINAC and then transfer the energy using coupled cavities to the accelerating beam. Okay, almost at the end. Also for circular colliders, energy recovery is proposed by our Brookhaven colleagues. They recently published a paper this year where they convert the FCCE into an energy recovery LINAC, kind of a bent ILC. You accelerate in 8 passes or so through 2 LINACs. You have multiple collision points, and then you decelerate. And with much less synchronization power, with 30 megawatt, they can get higher luminosity, and they can also go to higher collision energy. This is a timelines of future colliders developed with Vladimir Shiltsev and inspired by the European strategy process. You can see there's good hope in the 2030s to have an E plus E minus collider, because CEPC, ILC, CLIC, and FCCE, they all plan to start operation in the 2030s. EIC will come. And then for the hadron colliders, we have to wait, we have to wait a little bit longer, probably at the end of the 2040s is a good guess. And in this optimistic picture, also muon collider and plasma collider appear at the end of the 2040s. That brings me to the end. I would like to close with this quotation from JF Kennedy. We need the men and women who can dream of things that never were. So thank you very much. We need the young generation to come up with new ideas and also revive and reinvent the old ideas.
Okay,
thank you.
Thank you so very much, Frank. You went through from the beginning to all the way, even a few decades from now on, what type of future colliders might be, and that's an excellent overview. I'd like to thank you for that. We may have also time for one question that I'll ask you. So you talked about the future colliders, either lepton colliders and the hadron colliders, up to 100 TeV hadron colliders to a few TeV, perhaps a lepton colliders. But if you think about the following generation of colliders, it could be a few hundred TeV hadron collider or a few tens of TeV lepton colliders. To your mind, what kind of expertise in science and technologies are needed even if we want to dream about the following generation? Because the other ones you talked about, even though there are still a lot of R&D research and development needed, but there isn't any showstopper. But I'm talking about, so we can probably manage to do that. I want to think a bit more what the following generation. So what are your thoughts?
Well, there are many proposals for the following generation. One proposal is different types of plasma accelerators. Then there are accelerators on a chip using semiconductors, which may be more stable. They look a bit more similar to the present accelerators, but with very small dimensions and excited, maybe driven by lasers or by other means.
The question is that would they, be able to give a few tens of TeV lepton collider or a few hundred TeV hadron colliders? So especially with our young generation here, if there's something that you think of.
I think we have to look in different directions. There's also the idea to use crystals for acceleration, driven by X-ray lasers. It's the idea that Vladimir Shiltsev is pushing, which could also be quite interesting. Maybe crystals can be controlled more easily.
Right. So
and now we have X-ray lasers, but then maybe we need to go away from electromagnetic fields, and perhaps we can use other forces. For example, maybe we can use gravity for acceleration, or need to find another. At some point, we reach the limits of electromagnetic acceleration.
Conventional, your thought is that our conventional mechanism, we could make it up to next generation, but it's really we have to think outside of the box.
Yes, and people do look in different directions already. There are many colleagues look in different directions. Yeah. Maybe we need to look further and profit also from progress in other areas of science and technology.
Mm-hmm. Well, thank you. That's very valuable insight especially for our young CVB researchers. Okay, thank you again, Frank.
Sorry, I took too much of my time, but I thought I had more time because I started early, but I used it up apparently.
Because you had a lot of material to tell us. So let's go to our next speaker. We'll hear about RHIC and its EIC future. And speaker is Michiko Minty. So let me introduce her briefly. She received her PhD in 1991 at Indiana University and worked as a postdoc with the University of Michigan and SLAC. And she became staff member at SLAC in 1994, worked on both Stanford Linear Collider and the PEP2, this is the electron positron, the B-factory collider, as well as on the future linear collider at KK in Japan. From 1998 to 2005, she was at DAISY with the responsibility for DAISY lepton hadron injector synchrotrons. She also worked on the Tesla test facility, HERA, and XFEL. Following a 3-year maternity leave, she joined the Brookhaven National Lab as head of the instrumentation group in 2008. She is now deputy division head of the accelerator division and head of machine operations at the Collider Accelerator Department at Brookhaven. Michiko is a frequent teacher at USPAS, and together with Frank Zimmermann, you just heard his presentation, she wrote the book I mentioned earlier, Measurement and Control of Charged Particle Beams. Michiko was elected to APS Fellow in 2016, and she is presently serving past chair of the APS Division of Physics of Beams. Please welcome, joining me in welcoming Michiko.
Thank you very much. Thanks for the introduction and the invitation. And I was just thinking that I guess together with Frank and others, our paths have collided quite a bit over the years in the collider world. So I've been asked to talk about RHIC, the Relativistic Heavy Ion Collider, and its Electron Ion Collider future. I'm delighted to do so at this year's annual symposium. Again, thank you for the invitation. Just a view first about some of the high energy colliders in the United States. We have here on the West Coast, the Stanford Linear Collider, the E+E- Collider operating at 50 GeV that operated for many years successfully up and through 1998. The Tevatron, of course, it had a long and illustrious career there in Batavia, Illinois. It terminated operation in about 2011. And here on the East Coast on Long Island, we have the Relativistic Heavy Ion Collider, which started operation around 2001. It's based on a site that goes back about 100 years. It was initially a military site. It's been serving the science community with accelerators for almost 75 years by now. And as of now, the Relativistic Heavy Ion Collider, it's the only high energy collider in the Americas, and it's also the only high energy polarized proton collider in the world. So here's an outline. I'll give an overview, then talk about the RHIC facility, talk about the Electron Ion Collider, some select technology developments, and then close with a summary and outlook. So the Relativistic Heavy Ion Collider timeline, it goes back quite a ways, back to 1983, when NSAC, the Nuclear Science Advisory Committee long-range plan, included a Relativistic Heavy Ion Collider as the highest priority new facility. And then in 1990, the first idea of a polarized proton collider was discussed. These two concepts merged together into what's now RHIC. Construction started in 1991 with the first beam into the RHIC tunnel in 1/6 of the ring in 1998. Commissioning started just 1 year later and followed by the first collision of gold on gold taking place in the year 2000. The design luminosity of the accelerator was reached only a year later, and that same year polarized proton collisions took place. So for the past, since then, RHIC operates annually, sharing time between heavy ion collisions and polarized proton collisions. And one of the big features of the accelerator is it's very versatile, can collide ions of a wide mass range as well as protons. No electrons up to recently. And just want to point out that we celebrated 20 years of RHIC just here in this year. So this shows an overview of the RHIC accelerator complex. We have very old tandem Van de Graaff accelerators that can be used for generating ions together with a more new so-called electron beam ion source. The polarized protons are produced using an H- LINAC, and these that accelerates beams up to 200 MeV. And typical for all the big colliders, the energy of the ions or protons are accelerated up to high energy through a series of synchrotrons, including the booster here, the famous and old alternating gradient synchrotron. The protons, for example, are accelerated up to about 25 GeV and then injected into either one of two accelerators, co-circulating accelerators that can constitute the relativistic heavy ion collider. So their collider consists of two independently powered 3.8 kilometer superconducting magnet rings. They have about over 1,700 superconducting magnets total. And as I mentioned, that allows gold-gold, proton-gold, and proton-proton collisions, plus many ion species in between. at equal energies up to 100 GeV for gold-gold, for example, and protons up to 250. So there are 6 possible interaction regions. They were initially instrumented with 4 detectors for the interaction regions. So here's just a view of some pictures of the facilities. We start here on the bottom right. You can see one of the 2 tandem Van de Graafs. On the other side, you see the booster accelerator, which was built to support RHIC in the late 80s. The beams go into the alternating gradient synchrotron again. Here's the view in the tunnel there. Then they're extracted and brought through a transport line and here into the RHIC accelerators. On the top left is a view of the RHIC accelerator complex. You see 2 of the magnets, the insulating vacuum for the magnets. This will be the home of the future electron ion collider. And on the top right, there's some pictures of some of the normal conducting RF that's used to accelerate the beams. And just quickly, I mentioned that RHIC is the first polarized proton collider. Again, here's an overview. I won't spend too much time on this, although it is important because the EIC will allow for collisions between polarized electrons and polarized protons. But you see there's a lot of infrastructure here that goes into it. The polarized sources, so-called Siberian snakes and partial Siberian snakes, which are used to preserve the polarization as the beams are accelerated to high energy. And of course, a whole slew of different kinds of polarimetry to measure the polarization. So quickly, here's a view of the history, the commissioning era, which I already talked about. There's another era, 2 eras, which the main point here, and I'll talk about some of these, is that new technologies were developed and made operational to successively get to higher and higher luminosities. And the ones with the stars here, stochastic cooling, the high intensity electron beam ion source, 3D stochastic cooling, high intensity polarized ion source, electron lenses, oops, I don't think that should have a star, and also superconducting cavities. These will all be applied to the EIC technology. So we've built on 20 years of experience, and most recently, and we're using right now, new technology, so-called, well, electron cooling with bunched beams to support the basic energy science program. And then in the future, we have the Future Electron Ion Collider. So I'm going to go through the timeline, some of the key parameters, then just show conceptually how RHIC is transformed into an electron ion collider, and then go into detail of only some of the new features that will be added to the RHIC complex to realize the electron ion collider. So again, well, first of all, there was a white paper written in 2012 where an electron ion collider was proposed. It was commissioned by Brookhaven and Jefferson Lab as a follow-up to the NSAC long-range plan of 2007. And 2 approaches were pursued by JLab and Brookhaven. And in 2015, NSAC recommended that high energy, high luminosity, polarized electron ion collider as the highest priority for a new facility following the construction and completion of FRIB. So pre-conceptual design reports were drafted and recently evaluated together with cost and scope. And critical decision 0, which defines mission need for the country for an electron ion collider, was approved by the DOE just December of last year. That enables work to begin on R&D and on the preparation of the conceptual design report. And then following, shortly after the CD0 approval, the site decision was made to host, that BNL would host the EIC in strong partnership with JLab. So the next milestone is to release the conceptual design report, which would allow the release of project engineering and design funds. So here's a list of the key parameters as defined by NSAC for an electron ion collider. We need highly polarized beams, both the electrons and the light ions. That's required for studies of the origins of the spin of the proton and neutron. We need to accelerate ion beams over a wide range from deuterons up to uranium and lead. That's required to study gluons at high densities. We need a variable center of mass range. because you get more density of gluons, the higher the center of mass energy. The luminosity, of course, should always be high. We're aiming for 10 to the 34, just as comparison. Hera, the only electron-ion collider in the past, was more at about 10 to the 32 per centimeter squared second, so it's a couple orders of magnitude. And then in this design, we have more than one interaction region possible. So here are the maximum luminosity parameters for the electron-ion collider. This is the set of parameters that produces the highest luminosity. Notice that the energies here, the protons are at 275 GeV, the electrons at 10 GeV. The electron energy actually can go higher, but we've for the maximum luminosity, we limited at 10. That's based on synchrotron radiation power losses. So we have a number of parameters here. The challenging ones, we've got an arrow. So we've got beam currents of an ampere for the protons, 2.5 for the electron. The vertical emittances are quite small, 1 and on the order of a nanometer. The bunch lengths are very short, particularly for the protons. And these together, the short bunch lengths and small emittances, imply a very bright beam. And so that raises a challenge of interbeam scattering growth times, which need to be combated using cooling mechanisms. So here quickly, I'm going through how the RHIC is transformed from how RHIC is transformed into an electron-ion collider with these conceptual pictures. This shows the existing facility with the 2 rings, which we call yellow and blue just to distinguish as the co-propagating beams. To that, we add the high-energy electron storage ring, and that will store the electrons that collide with the ions in the existing facility. And to get the high-energy electrons, we add an electron injector complex, and we use what's called a rapid cycling synchrotron, which I'll talk about next. As is an injector, a high current polarized electron source, and an injector LINAC, SLC style. And then finally, we have strong hadron cooling to complete the facility. So that's based on what is sometimes called coherent electron cooling, but there's an alternate solution that's very low risk, which we're talking about these days, that involves using the other unused existing RHIC accelerator as a full energy injector for the hadrons. So this, just before going into the details of some of the new features, shows a cross-sectional view of the RHIC tunnel. We saw a picture of the cryo stats there, and the added accelerators are shown here. There's the rapid cycling synchrotron that accelerates up to full energy, the electrons for injection into the main electron storage ring. So I'm going to talk about the new features that would be added to make an electron-ion collider. One is the electron storage ring. It has an energy range of 2.5 to 18 GeV. Since it's one of the and at present it achieves that using superconducting RF. One of the design challenges is to maintain the emittances at all energies. So that's achieved using a flexible design of a magnetic lattice comprising 6 photo arcs with adjustable phase advance, so it can be adjusted to achieve the desired emittance at these different energies. Another challenge is to preserve the high polarization and to have fully flexible spin patterns. So for the experiments, the polarization can be of bunch by bunch can be different. So how is this achieved? That's achieved using a polarized electron source and polarized preserving pre-accelerators. To orient the spin at the interaction points, we use solenoid-based spin rotators, and bunch replacement is required at a 1 Hertz rate to avoid stochastic depolarization. So this is an interesting effect. Electrons stored in a ring, we're injecting fully polarized electrons with about 70% polarization, but the equilibrium polarization in the ring, if it were just left to slowly build up, is only about 50%. In addition, the experimenters would like to have the polarization of different bunches, either, for example, vertical up or vertical down. And the electron polarization tends to anti-align with the main dipole fields. So over time, through stochastic processes, half of the, or some of the electrons, their polarizations will start to precess. So to remove all these systematic errors, the idea is to replace the bunches at a 1 Hertz rate. So to do that, there's some modest technology to develop. So the idea is that we're going to accumulate bunches in the rapid pre-injector called the rapid cycling synchrotron, and then is shown here with a beam electrons traveling from right to left. For example, you have introduce a closed orbit bump. However, this would be fine to then extract and inject the extract a bunch to the dump, and then accept another bunch, except due to the nonlinearities that are typical close to the injection septums. So to do that, we have to provide additional fast kickers that act in unison with the slow kickers to achieve that, to extract one bunch and then immediately inject another bunch, which also has advantages with regards to beam loading transients. And since this is a CBB research theme, superconducting RF and future high energy accelerators, I just showed this view. This is still in development. I believe the frequencies, well, the design are changing, but the frequencies are based on being harmonic multiples of the existing frequencies in the hadron complex. So to get the highly polarized beam for full energy injection into the main electron storage ring, we need to accelerate the beam from low energy, which is about 400 MeV, up to the desired extraction energy. So the extraction energy is going to be determined by the physics program, and the range is 2.5 to 18 GeV. Here the design challenge is preserving the electron beam polarization during acceleration. And so that's achieved using a spin transparent rapid cycling synchrotron. So a word about this, the spin dynamics is governed by the famous Thomas BMT equation, which is shown here. S is the spin vector, and G is a constant. It's the electric geomagnetic anomaly. And as you can see that the spin, if it encounters any transverse magnetic field, it will change. So normally the spin is aligned with the vertical fields of the dipole. However, due to orbital motion, for example, the particles can experience horizontal fields if going off axis through quadrupoles. And so that can cause the polarization to not be preserved. So what needs to be done is that you avoid the spin resonances. And the conditions for the spin resonances are given here for the two leading order spin resonances. They're called imperfection resonances, which are due to dipole rotations and quadrupole misalignments and depend on the closed orbit of the beam, or intrinsic resonances, which arise primarily due to vertical betatron motion, where here Q is the betatron tune and P is the superperiodicity of the lattice. So the concept behind the rapid cycling synchrotron design is, in addition to it being rapidly cycling, it's spin resonance free. Here again is the resonance condition. And so for the energy range from injection to full energy, 400 MeV to 18 GeV, the product of this anomalous gyromagnetic factor times the relativistic factor is in this range. So if you can make resonance conditions the leading orders that are outside of this range, then you have a spin resonance free lattice. So by designing a lattice with a periodicity of 96 and a betatron tune of about 50 or higher, for example, then the strongest imperfection resonance occurs at 46, which is outside of this range, and the strongest intrinsic resonances occur also outside of this range, around 50 and 46, minus the fractional part of the vertical betatron tune. So this is the clever idea behind this new concept. And here on the left is shown the ideal circular ring that's got a nice periodicity of 96. That's not achievable in the existing RHIC tunnel because the existing accelerator has got 6 sides. So the idea is to make spin transparent straight sections, spin preserving straight sections here. That's been done and designed, and here's a simulation result that shows the amount of transverse polarization. The scale here is 100% down to 93% as a function of beam energy, and the blue curve corresponds to a rapid acceleration duration of 200 milliseconds, which is, I think, the present design. Moving on to strong hadron cooling. Let's see, there are 2 options being considered. One is coherent electron cooling with a free electron laser amplifier or microbunching amplifier. And the second is full-on energy injection and with a conventional electron cooling using the second unused RHIC storage ring. So I know there's a lecture on this afternoon, so I won't spend too much time on this, but just briefly, here's a concept of electron cooling with a free electron laser amplifier. I like to think of this as stochastic cooling, but where the pickups and kickers are replaced by electron beams, where you introduce an energy modulation so that an energy deviation, so that in a sense, the protons or ions are compressed by the electrons due to, in much of the same way as a bunch compressor works. So much of the design focuses, variants, I should say there are multiple variants in the moment, focuses around this section in the middle. The goal of any design is to get short cooling times, as I mentioned, to counterbalance the strong interbeam scattering. So here's one concept. It's not necessarily what will become the final concept for strong hadron cooling in the EIC. Notice it starts with an electron source and it has an energy recovery LINAC. So it has the modulator section. So in this section, the beams are propagating. It has, in this case, showing a microbunching amplification scheme for the electrons traveling right to left, and then they're merged again together with the protons in this kicker section. And in that way, the beam is cooled, the electrons return, and then they continue through the recirculating LINAC. So the straight section there is about 200 meters in this design. The alternative low-risk approach is to use the existing RHIC accelerator, and there's only one modest novelty here, and that is, so the idea there is that you use the existing RHIC accelerator to bring the beams to full energy, then you need to transfer those into the accelerator that is used to collide with electrons. So in this idea, you have bunch replenishment which is accomplished using a series of kickers to simultaneously extract all the bunches from one of the hadron rings and put it into the other hadron ring. So you simultaneously extract from one and inject from the other. And in that way, again, keep the total, keep beam loading to a minimum. So moving along to select technological developments. These are all developments that have taken place or are taking place and will be applied at the electron ion collider. Start with bunch beam stochastic cooling, which has a long history. It started already in 2007. So what's novel here is that this is going up to very high frequencies, which is not the case for the conventional stochastic cooling of the previous years, which acted on DC as opposed to bunched beams. So this is a view. It uses now we have stochastic cooling in all three planes, longitudinal and both transverse planes. There's a lot of technology that went into this. There are pickups as shown here. There are kickers that open and close to accept beams, large beams at injection, and then close once the beam is stored for then cooling. Here shows some of the kickers down on the bottom right. And then these signals, the gain is kept high by sending the correction signals through the air through microwave links. And with this system, we have about 3 gigahertz bandwidth with cooling times on the order of an hour. For coherent electron cooling, we have an R&D facility built into the RHIC accelerator complex. Up until recently, it had a layout that looked like follows. It has a superconducting photo gun and cathode. Here, it's using a superconducting LINAC over here. And here in this scheme, we used the electron beam was accelerated up to about 15 MeV, I think, and then there was an FEL concept for getting the modulation for the subsequent kicking and cooling of the ion beam. So we had to remove that because the aperture of these wigglers was too small to run in parallel with the ongoing basic energy science program. So what we have now is a plasma cascade amplifier based cooling channel. So we're using the existing electron LINAC, and we have this in place. So this is work in progress. It runs about 2 days a week. It's running today. And just last week, the electron beam parameters that are required for the next steps to show the so-called imprints and density modulations on the ion beams. Those are next goals, but the parameters were just achieved here last week. So bunched beam electron cooling, this is a facility that is in routine operation. We're using it right now this year and next year for the basic energy science program. And what you're seeing here, this is data from Tuesday that show the luminosity rate at the star detector. This is showing the evolution of the bunch lengths in the two rings, and this is showing the evolution of the vertical beam size in the two rings. You can see they're all being nicely cooled, and that keeps this event rate high. Here is show on the bottom right shows the integrated luminosity with and without electron cooling. So you see there's a significant increase. For the electron ion collider, we need a high current injector. This facility, once its use is completed after the basic energy science program, will be converted into a high current injector R&D area. And then finally, since polarized electron sources are another one of the CBB's research areas, I like to mention that we have a facility that is located at Stony Brook University, where we plan to demonstrate a very high charge per bunch electron beams at 1 to 2 hertz repetition rate initially. These are the requirements for the EIC. The lasers and such are set up to go to much higher repetition rates for cathode studies. This is based on the JLab inverted gun and has very high vacuum requirements to preserve the cathode. So this first beams are expected from this facility next month, and it's planned to do many R&D activities, mostly initially focusing on cathode development and quantum efficiency lifetime. So moving to the summary and outlook, RHIC is the first heavy ion collider and also the first and only high energy polarized proton collider. Over the last 20 years, RHIC has operated with unparalleled flexibility in collision energy and ion species. The science case for the electron ion collider was approved by the DOE in December, with BNL chosen to be the site just earlier this year. And the next milestone is to complete the CDR, which we're hoping to finish this year. So many major technological advances in particle sources and beam cooling have been demonstrated at our facility in collaboration with many, and will be used at the electron ion collider. So this is just a schedule showing where we are. Right now we're in the midst of the so-called beam energy scan using the electron cooling system I just described. Actually, I forgot the overview slides, or maybe I jumped past them, but that's okay. And so we are, we'll finish that up in about another year. And then we have presently ongoing a detector upgrade and plan to return to polarized, high energy polarized proton operation. And then here below is shown the EIC timeline, shows research and development, and then eventually installation of the infrastructure, the procurement, fabrication, and test. We have a period right now of 3 years where we are installing. The pre-accelerators will continue to operate. We have a number of other research programs. And then commissioning and pre-ops is scheduled. Early finish is expected in June of 2029. Right, with 1 year afloat. So that brings me to my last slide, which is acknowledgement and thanks. I'd like to thank everyone in the Collider Accelerator Department whose collective accomplishments are presented in this talk. I'd like to thank also all of those who have supported our efforts through many external reviews. And some of our speakers today are shown in this picture, standing in front of the review of the pre-conceptual design report at Brookhaven in 2018. And lastly, I'd like to thank everybody for your attention.
Thank you so much, Michiko. There's a wonderful presentation, and as you pointed out, that there's quite a bit of connections and synergy between all the RHIC and EIC to CBB. So that's very nice to know that. One question, sort of you have an accelerator team, both the scientists and engineers, for example. Could you introduce a little bit, just to give some sense of the team? They have to not only operate, but for future, you have to develop and do science research. So it might be helpful for especially our junior members of CBB.
Right, so in the accelerator department, we have right, scientists and engineers, and we work extremely closely together. Sometimes the scientists, will be working on the design reports, but that's always in close collaboration with engineers, because really we have to push to see what can be realized, and what we're always pushing to the limit, right? To and the goal of the brightest beams, the coldest beams, the highest luminosities and things. So it's always in very close collaboration. Even the accelerator designs are driven largely by discussions with the engineers. So we need to understand limitations across the board. Just to make an example, so I mentioned that we have very high current proton beams. So this is quite new, and we've investigated how to overcome the cryogenic heating that could be caused by such beams. So that requires collaboration with the vacuum groups. We're investigating amorphous carbon coatings or sleeves. The LHC has been down this path, and really the choice and the parameters that ultimately can be achieved will depend on this close collaboration with the engineers. Similarly, with the RF groups, the superconducting RF, I didn't mention this, but as Frank mentioned, that's typically been superconducting RF in the electron machine. So we are kind of proud that we finally did get a superconducting cavity in the proton hadron machine. But that's been a huge effort, and will come back in the S-Phoenix era. The collaboration just it goes on and on. The instrumentation, really, how well can you control how well can you measure the properties of the beams? How well can you control the positions, the sizes, and so on? This is in collaboration with the instrumentation groups and with the controls hardware for the timing, and control software as well for feedback systems. I'd say that there's no engineering group with which the accelerator scientists do not collaborate extremely closely.
Mm-hmm. Yeah, that's great. So roughly, how many accelerator scientists you have at Brookhaven?
Not speaking for the light source community here at Brookhaven, I'd say we have on the order of 45 or 50, mm-hmm. and maybe 3 times the number of engineers.
Mm-hmm. Great. So now I'm gonna ask Philippe, our symposium host. Philippe, do you have any questions to Michiko? Okay, I'm not hearing from Philippe. So there was one question actually from chat box. Are there challenges to recruit and maintain future accelerator talents? I guess this is also we'll discuss more also later panel session, but you can say a few words too.
Well, I will say that for the electron ion collider, be on the lookout. Right now, we have to get through the CDR, and at some point get the approval to hire. And we are certainly expecting that we'll need to hire a lot of people. And we are especially interested, not just for the EIC, but also in the existing accelerator division, in hiring young people. It's typical across the laboratories, I would say, that the accelerator folks are, tend to be on the older side. So we really need to bring in young people. And, right now is a wonderful time because at least at Brookhaven, we're going through and upgrading all the existing facilities while at the same time starting new developments for the EIC. So it's an exciting time, and I think it would be very rewarding for young people. I do have a concern because of the most recent COVID. The news reports say that young people really like to be physically on site, and I think that's right. In order to be able to walk into somebody's office and have a chat and get the ammunition you need to go to make next steps in your research. So that's a problem that we're starting to think about, but we'll just have to see how that evolves.
Yeah.
But that's a concern for me, that without enough interaction, I mean, real physical interaction, that could be disillusioning for the younger generation. And I really don't want to see that happen.
Mm-hmm. Maybe I have one more question. What do you see the biggest challenges for EIC, both the scientific challenges and technical challenges?
Scientific challenges. I haven't really talked about like the detector design yet, but the whole interaction region is a very complicated region. And in fact, there's an area where, in my view, we need more involvement, a new generation of ideas. It's a very complicated area because the interaction region design requires a very, very broad knowledge base that includes understanding accelerators, the beam-beam interaction issues, and also the detectors. There are lots of trade-offs that need to be made. So I think that's an area that is quite challenging. It's also challenging because they are big experiments in themselves with often hundreds of collaborators, so there's that aspect as well. And then from the technical standpoint, we have not yet demonstrated this strong cooling. So we have a 3-year program going on right now, starting this year with the plasma cascade concept, but that hasn't been proven. So, you know, we're working on alternate options. So that's a risk factor, but that is really needed to get to the highest brightness beams. Which of course you need for the highest luminosities. So we're trying to work on scenarios that get the 10 to the 34 luminosity as potential backups to the coherent electron cooling, and trying to design at the moment to be flexible to accommodate all possible variants. But that's the one area which we really need to see progress on, I would say. Of course, for the other scenario, you know, in both, actually another area is the 100 milliampere electron beams. So we need that for conventional cooling with the reuse one of the RHIC accelerator rings. And then I didn't get a chance to go into the challenges of the electron source itself. So we would like to use the inverted gun design and have that in development, but we're trying to achieve much higher single bunch currents. So we need to get much higher single bunch currents, and then in addition, we need to have polarized beams. So there's a lot of cathode dynamics that need to be proven. So that will be a very, very interesting area of research. It involves other fields of science as well, so the materials. So that will be very interesting, and it's very interesting to see that the Center for Bright Beams is working on these topics as well.
Great, thank you again. You know, one of the issue about COVID is because if we were having this meeting in person, we would give a big round of applause to of course, the Frank, and also to you. So you don't hear that, you know, loud the applause. But imagine that we are all doing that. Okay. All right, fantastic. So let's move to our next speaker, Elena Fall from CERN. She's gonna give a talk on machine learning and colliders. So let me give a brief introduction of Elena. Elena, are you there? Ah, okay.
Yes, I'm here. Yeah, I hope you can hear me. Yes,
Yes, I can hear you.
okay,
Elena
perfect.
received her master's degree in computer science from Cousineau University of Applied Sciences in 2017. Her work at CERN studied and continues now in the beam optics measurements and corrections team, where she was first involved into software development as a technical student. At the same time, finalizing her master's thesis project on first investments of applying machine learning to beam measurements and control at the LSC. The potential success of a machine learning application has been welcomed by the group. So since 2018, she studies at CERN as a PhD student in accelerator physics. affiliated with the University of Frankfurt. Her PhD project is focused on identifying suitable machine learning concepts for various accelerator problems, including implementation of a new machine learning-based techniques for beam optics measurements and controlled at the Large Hadron Collider. Please join me in welcoming Elena for her machine learning and colliders talk.
Thank you very much. I will now start to share my screen. Hopefully. Yes, is it right now?
Yep.
Okay, so I will start with my talk. First of all, thanks a lot for inviting me to speak today about machine learning. So I will start immediately with an introduction to the machine learning topic. So what is actually so important and what makes it so advantageous to use machine learning? So there are several tasks which are extremely easy and obvious for us as humans to solve, but which are difficult to solve in, let's say, traditional ways, meaning by building rules to make a decision. So let's see it on a very simple example of classifying a cat. So for us, this object is obviously a cat, and we could say, okay, to classify this object, we could build rules and say the object should have 4 paws, 2 triangular ears, whiskers. But what if the object looks like that? So for us, again, it's very obvious that it's a cat because from examples, we know that cats can have different shapes and look differently. But how do we build general rules to classify all possible kinds of cats? So since we can learn from examples, there is a concept that machines can do it as well. And machine learning has been widely applied in many different areas, ranging from recognition of faces till, for example, AlphaGo, which is a deep neural network which was trained to play a game Go and which surpassed the best Go player in the world. Nowadays, machine learning is also widely used in the medical research. So a very hot topic is, of course, the COVID, and their machine learning has been also applied, for example, to identify infected areas in the X-ray images of the lungs. And also, of course, machine learning is a very common approach in energy physics, where it has been used to dark matter search, to recognition of exotical particles, and many other fields. So all machine learning methods, they have in common that they can improve with experience and learn from examples without being explicitly programmed. And explicitly programmed meaning by providing rules. So there are 3 main concepts in the research area of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning can be applied in case we have input and output pairs, meaning we have some input and label output which we can use in order to train models to make prediction on unseen inputs. And in case we only have input pairs available and we want to just extract some structures or patterns from the data, so we want to learn something from our data, there we can use methods of unsupervised learning, such as, for example, used in detection of spam, or we can also group some objects by using some clustering methods. And the 3rd concept is reinforcement learning. So here we have no training data again, and here we have one model which tries to build an optimal sequence of decisions based on the response from another model. And this is also extremely widely used in robotics. So let me show you again on the example of classifying cats. How does the learning work in practice? So the supervised learning in this case. So the usual pipeline of applying machine learning, of building a machine learning framework, is we have to collect the examples. and then labeled examples. And then, of course, we cannot just process this picture how it is. So we need to extract the so-called features. So the data properties which are then used to make a final pre-prediction. In this case, so we do some image processing, we extract the features, and then we pass it as input to the model. The model has to be trained, tuned, and validated, and then we can say if the object is a cat or not. So in a bit more details, so for example, supervised learning can be approached with using neural networks, which are basically functions of output, which is constraint of the weighted input vectors, and some activation function, which can be a nonlinear function, which is in most cases a nonlinear function, in order to capture the nonlinear correlation between input and output. So, and how does it work actually? So as I said before, we have training input data and training output data. So these samples are passed through a model. So we take the input data as the input of the model. The model predicts an output, and this output is then compared to the actual true output of this training sample. And then we can compute the loss, for example, the mean absolute error, and then based on this loss, trying to minimize it, we can adjust the weights and biases of the network. And like this, we built a model which will be general enough in order to satisfy the input and output relation between all the samples. So of course, there is a question, how much training is needed? So actually, no perfect model is needed, because a very perfect model, a very complex model which fits perfectly to training data will end up being a lookup table, which you of course don't want, since we want to make predictions of unseen data. And of course, too simple models, they will underfit, they will be too different from the true outputs. So we need to find a trade-off between bias and variance of the model. So of course, machine learning is more than just neural networks. There are many more other methods, for example, to build classification and regression models. We can apply just simple support vector machines or other least square methods, which are much simpler than neural networks, but still can do their job. There are also techniques to reduce the data space. Also, there are decision trees which can be used for classification and regression tasks. In this case, we built a sequence of thresholds which we learn from the data, which we don't build ourselves. And also there is clustering, which can be used for group or to separate data and to find hidden patterns in the data. So machine learning is about learning from the data and not about applying particular methods such as neural networks, which maybe is the most famous one, but still there are many more other methods, which I will show later on the examples also. So what is the motivation to use machine learning in particle accelerators? So machine learning is a powerful tool in data analysis, which has been shown in many other fields. And of course, in such tasks as optimization and modeling of our machines, there are many traditional tools which are very great, but still there are some limits. So we need to identify these limits and try to find out if machine learning can help or not. So, and especially in the cases when we have to deal with previously unobserved behavior of our beam of the machine, if you want to extract some knowledge about what we actually see, or in case we have a lot of optimization targets. So in this case, also machine learning methods can surpass the old methods. And sometimes we don't actually know what are the thresholds or the optimization targets. So also particle accelerators are usually consisting of nonlinear interacting subsystems which rapidly change. So in all these cases, machine learning methods can help, since they can learn arbitrary models from given data without provided rules. So now I want to show how widely applied machine learning methods can be also applied in our area. So here on the example of image processing and convolutional neural networks, which are some special kind of neural networks. So here is an example how one can take a picture and then predict a probability of an object being in the picture. Let's say a bird is in this picture with 98%. So the same technique, convolutional neural networks, has been applied by, for example, ORNL in this work, where they took the image of a beam profile and they combined it with some other data in order to build a hybrid neural network consisting of a normal neural network and a convolutional neural network in order to predict some properties of the beam from the beam image. Another example is reinforcement learning. So this machine learning methods is widely applied in robotics. Maybe many of you have seen the videos by Boston Dynamics where the robots learn how to walk, jump, or avoid obstacles. So the same concept has been used also to take control over beam. In the cases of instabilities which arise from the interacting of the bunch with its own radiation. And in this case, the agent takes actions in form of modifications in RF, and the response of the environment is the CSRR signal. Another example is that in machine learning, there is usually a concept of so using average vote of several models in order to make a more robust prediction of some task. And the same concept of combining several machine learning models has been used at the LHC to build framework to automatically align the collimators. So previously, we needed an expert in order to say during the procedure of alignment of the collimators if the collimator actually has touched the beam or not. And currently, the standard framework at the LHC to align the collimators is a machine learning tool which consists of several modules which classify based on the input data if the collimator has touched the beam or not. And the average vote of these modules is taken in order to stop the collimator alignment. Now I will speak a bit more about applications of machine learning in beam optics measurements at LHC, since this is the area where I'm working on personally. So first of all, why do we need to control the optics? I will not introduce the LHC now because you have heard it already in Frank's talk. So of course, in LHC, we want to have a high luminosity, which is also balanced between the different experiments. And for this, we have to control the beam size. And also the imperfections in the beam optics, they can lead to machine safety issues. So how the optics is measured? The optic is measured based on the signal of beam position monitors, which are the instrument which record the position of the beam passing around the ring at several thousands of turns. And then we perform optics corrections aiming to minimize the measured difference between the optics in the machine and the design optics by changing the strength of the quadrupole magnets. So, and there are three tasks which are solved or potentially will be solved using machine learning. One is detection of faulty beam position monitors. So, of course, since the optics measurements rely on the BPM signal, the BPM signal has to be clean and there should be no faulty signals because they will perturb the computation of the optics functions. So we need to identify the faulty signal before we compute the optics. Second task is prediction of magnet field errors. So the measured deviation from the optics to the design is caused by the magnetic field errors, and we want to estimate the currently present errors in the machine based on the measured optics. And the third small task is the issue of missing or noisy measurements. So in case a BPM is faulty, so the signal at the location of this BPM is missing, how can we reconstruct the signal from this BPM, or how we can reduce the noise in the measurement. So I will shortly introduce the first task, the detection of BPMs, of faulty beam position monitors. So as I said before, in the presence of faulty signal, the measurement of the optics, the computation of the optics function is affected in a negative way, and there are some cleaning techniques already available, but they are not perfect. So we still need some other method in order to clean the BPM signal. And there we have applied the technique called isolation forest, which is an ensemble of decision trees. So how does it work? So basically, one takes random splits on the data, trying to isolate each point in one region. So as you can see here on this example, an outlying point is much likely to be isolated with just one split than a core point, which, for example, here you need just one split to isolate an outlier, or 3 splits to isolate a normal point. So this is how this technique is able to identify anomalies in the data without having any rules or thresholds to say what is the difference between normal point and anomalous point. So how we apply it at LHC, we take the BPM measurements, which are about thousands of BPM measurements, and we don't know which are faulty and which are useful for optics measurements. So then we extract the properties of this BPM signal, which you have to do anyway in order to compute the optics functions. And on these extracted properties, we perform this method. And so here you can see an example of identifying faulty signals. And then after excluding the BPMs which were identified as faulty by this method, we compute the optics, and then we can see that using only the technique which was used before, the SVD, there were many outliers which can be still observed in the beta beating. And if we apply isolation forest on top of it, then almost all the outliers are not there. So this technique is fully integrated into optics measurements at the LHC and has been used for 1 year in the latest LHC run. So second example is the estimation of quadruple errors. So this is a bit more difficult to explain, but I will just try to briefly introduce it. So here the concept is that we want to obtain quadruple errors from the measured optics, because there is a correlation in these input and output pairs, since the optics errors are introduced by the quadruple errors. So we want to build a regression model and train it using supervised learning. So one could, of course, train it on available measurements and available corrections, but there are first not enough measurements to train a model, and also we don't want to have the same results as in the previous corrections. So we built a data set from simulations. In the simulations, we generate randomly individual quadruple errors and perturb ideal optics with the errors. And then the output of the simulations are the perturbed optics. And this is then the input of the machine learning model, which is supposed to predict the individual quadruple errors. And we have used just a simple linear regression as baseline model because it's fast to train and easy to interpret. And this already allowed us to receive these results, these promising results. So first, we can validate our model on the test data, on the simulations, and there we can just compare true simulated magnet errors and the model output. Here we have 16% of systematic error. And then we also compared, we also applied this method using actual LHC measurement, where of course we don't know the actual quadrupole errors which introduce the measured optics errors, but we can use the predicted optics errors from the machine learning model in order to simulate the optics, and then we can compare the simulated optics with the predicted errors to the measured one. And this gave us the RMS error of 5%. So the third concept is denoising and the reconstruction of the phase measurements. So the phase advance between the BPMs is the main signal property for the computation of the optics functions. And of course, if there is some missing BPMs and the phase advance measurement is not available, it will be helpful to provide the signal by the reconstruction. And also the prediction of the quadrupole errors, the previous example. So the accuracy of the model, it depends highly on the noise in the input data. So if we reduce the noise, the prediction of the quadrupole errors will be also better. And that we have achieved using an autoencoder neural network, which is a special kind of neural network used to predict in the output layer the same as was provided in the input layers. And by using the hidden layers, in the first half you can encode the information from the input, and second half is the decoding of this input. So this allows us to remove the noise and also to predict the original phase advance. And these are the results which we achieved for now on simulations. So the noise could be reduced by a factor 2, and the accuracy of the reconstruction of the phase advance is 1%. Oops, yeah. So which concepts are potentially useful from my opinion, but not widely used yet, at least to my knowledge, not. So one is transfer learning. This is the concept of training a model on one problem and then applying the same model to another task. It can be like completely different task after a short retraining. Of course, the retraining takes much less time and much less data is needed. So one can take advantages of the previous efforts. Another concept is inverted models. So in this case, one could train a neural network or any other model to predict some output targets. And then one could flip this model in order to provide the before used as output targets properties as input, and then get the other properties as output. So this can be, for example, used if we want to predict some beam properties which cannot be measured. And another application could be also the processing of text data. So for example, the logbooks, they contain a lot of unstructured information, which can be structured applying some data mining or machine learning tools. And this information can be, for example, used to prevent some instrumentation faults or to build some alert systems. So in the end, I would just give some practical advice. So of course, the key of applying machine learning techniques is your data. So feature engineering, which is building and extracting the properties of the data which can be used to train your models, is extremely useful. And also one should always start with simple models before applying some fancy techniques as neural networks. And also, if one wants to introduce the machine learning tools, of course, it's important to think about if the available infrastructures are extendable, or if, for example, the whole new control system will have to be built in order to make use of machine learning tools. And here are just some frameworks to use in case one wants to build some machine learning frameworks. And in the end, just a short summary of where can we use machine learning in particle accelerators. So as you have seen on the example of faulty BPMs, it's the detection of instrumentation failures. It can be also beam control as example of reinforcement learning, or prediction of quadruple errors. Of course, also the optimization and the automation, these are the traditional ways to apply machine learning. And also diagnostics of some properties which cannot be directly measured. And of course, by building such tools, we always have to define rather a narrow task instead of trying to build a tool which will optimize the whole machine at once. And also we need to be clear about the performance measures. So of course, one can validate machine learning model from the machine learning point of view, but also we need to see what we gain in beam size, in the pulse energy, and so on. And also machine learning, of course, is not meant to replace all the previously available methods, but there are some cases where machine learning can really be very helpful. For example, when no analytical solution is available, or if no direct measurements are possible. So it's highly important to really identify where the effort will pay off. Thank you very much for your attention. This is the end of my presentation.
Thank you very much, Elena. It was wonderful, the overview of what's happening in LSC. If you go back to the previous slide, just one
yes.
slide back.
Yes.
One, yeah. First of all, you know, the machine learning application or machine learning is quite popular in our CBB, and there are many, especially our the early career students, postdocs are very, very passionate about this topic, and so it's very useful for us. You said that these are the 4 areas that you can imagine that we can use the machine learning. In its CERN LSC system, are they all of these are the LSC uses machine learning for all these cases, or still?
So actually, like there are many techniques now under investigations or in the developments. So which is currently used is the detection of instrumentation failures, the BPMs, and the collimators alignment. So these 2, yes, are actually in use. And the others, I think there are some experiments at Awake beamline at CERN, so not directly at the beam optics at the LHC, but at CERN there are more examples. So especially in reinforcement learning, I think there are many efforts of building reinforcement learning for SPS. So actually, yes, I would say most of these topics are covered.
Mm-hmm. That's great. Okay, so let's see if there are any questions from our CBB members or visitors as well. You can raise your hand using a raise hand button.
There's one in chat, Yanki.
Okay. Sadhar, you wanna ask questions?
Sure, I didn't know how to raise hand. Thanks, Jan.
Okay.
So anyway, I posted my question, Elena. First of all, thanks for this very new and excellent, summary of what is happening and new ideas. My question is, like, mostly people are interested, has ML improved any existing, numbers? Like, in particle physics, we always say we improved our, background by 30% or 20% using machine learning. So are there any such numbers? I know it's all new, but if there are any that would be catchy.
Yes, there are actually some numbers. So, for example, again, in the collimation alignment, so before, one would need like several hours to align the collimators. And nowadays, I think in the last experiments they did, they just needed like 58 minutes. So it was indeed a big gain. And also there are examples, I think, from, I don't remember exactly, but it was a FNAL machine where they could also increase the pulse energy. I don't know exactly the numbers, but it was also like order of magnitudes. So mostly the biggest gain is usually the time. So because of the automation which can be achieved by applying machine learning techniques.
But you also mentioned that noise got reduced by a factor of 2. So that's beyond the time, but it's quite...
Exactly, yeah. But that was done on simulations, so that's why I didn't highlight it that much. But yes, on simulations level as well, also the noise can be reduced indeed.
Great. CBB students. Any questions from our students? How about postdocs? How about senior people? Are we okay? Usually we are not that shy or quiet. So I'm surprised. Okay, so since we have about 9.
I have a quick question.
Oh, great, go ahead.
Yonki. Elena, nice talk, really nice applications also. For your autoencoders, I know there are different types of autoencoders, including variational autoencoders. Did you have to do anything to make sure that your hidden space is useful for kind of ensuring that you can do manipulations also in the hidden layer to kind of explore your space of whatever the term was you used for those?
Yes, so actually I didn't use the variational autoencoder, the one you mentioned, but I just used a simple one with just 2 hidden layers, I think. And yes, so you can actually plot the representation of the hidden layers. At least, for example, if you use Keras or TensorFlow, it can be done because you can extract the weights of the neurons and you can see what is the representation of the hidden layers. But to know actually if it's useful, the representation of the hidden layers or not, one could just try to reduce the number of layers and see how the performance of the model changes. So this is actually also useful if you want to find this bias variance trade-off, like the complexity of your model. So you can, for example, like plot the number of layers and the accuracy. On the test set, it is also very important that you always need to split your data into training and test set. So yes, instead of using all the data as training data. So of course, there are many details which are very important to keep in mind when you apply it, but I didn't have time to speak more about machine learning details. I wanted to present more examples to motivate people to use it more.
Thank you. That's helpful.
Thank you. Thank
you.
you.
Ryan, you have a question. Go ahead. Ryan? Oh, he has no voice, so I'll read it to you. Is there a specific algorithm for determining the model complexity?
To my knowledge, no. And this is actually also one of the main issues in machine learning. So actually, the design of your model is very specific, depending on the task where you want to apply this model to. So this is like, that's why many people say like there is no free lunch in applying machine learning. It's not a like magical tool. Like, of course, you still need a lot of effort, and usually most of the effort is spent on preparing the data and also to find the right design of the model. So this is actually indeed the biggest issue in applying, especially neural networks, because they're very complex and can be very large or very small, and one have to really investigate what is useful and what is less useful.
Mm-hmm. So I think another, Elena, the comments or questions related to your last comments, you know, we have to understand when and where this machine learning will be beneficial. So this is something also CBB would like to categorize all that. So it might be good to really understand from that specific point of view. And so how, is there any effort to, you know, collecting all the information from all those who are doing machine learning, especially on accelerators, and trying to figure out, or trying to categorize the machine learning or not, the applicability and benefit. Is there some specific effort to go in that, to understanding that?
Actually, yes. So I don't know any people who work like particularly only on that. But for example, there has been in the last 3 years machine learning workshops, machine learning for accelerators, and there usually like people exchange what they have been doing, what was useful, what was less useful, and maybe I can send later some publications around which were like the summary of these workshops, because like usually there are some summary papers on that. So maybe it would be useful, or maybe you know already such papers. So actually, yes, like people really try to exchange the efforts and to reuse the knowledge.
Okay.
Because indeed not everything is useful. Of course, some efforts they fail, and this is also normal. So yeah.
Yeah, I see that Adi posted the webpage. Maybe this is the one. But in any case, Elena, if you can send us the link of the paper, that is very helpful.
Sure.
Now, how about the questions to all the three speakers, Frank and Michiko and Elena? Okay, so if not, we can end our morning presentation. And I'd like to thank everyone who gave brilliant talks and with a nice conversation and discussion. So let's give them a big round of applause. Very well. Okay, so I think now we move to a break session. It goes until, so we have about 30 minutes or 33 minutes, go until 1:50 Eastern time. You can keep it open, and this will support to be just either you can have a lunch or snack, or we can chat. So you can do whatever you want, or you want to take some break and come back, that'll be fine too. So let's use this time again, eating and chatting. Okay.
Okay, so it is my pleasure to introduce what has become a tradition in CBB, which is the poster blitz. We give all of our graduate students 1 minute to get you excited about their poster, and then they get cut off. Usually this is the highlight of our symposium. I hope it will be again today. Only this time we're going to do this virtually in a pre-recorded format just because of the issues with Zoom. And so with that, here are our graduate students.
Hi everyone, my name is Jay. I'm a grad student at Cornell working on studying femtosecond scale photoemission. Monte Carlo techniques have been widely used to study photoemission processes in the photocathode community. In this work, we are studying the photoemission process in gallium arsenide under high fluence femtosecond scale laser pulse. Unlike conventional Monte Carlo studies, carrier non-equilibrium dynamics is crucial in the femtosecond timescale, thus requires us to calculate hole dynamics. The two figures in the slide show the calculation results of hole drift velocity under high extraction fields that are determined by various carrier or carrier phonoscatterings.
Hello, my name is Zilanjan Banerjee. I'm a new member of CBB working on quench imaging for SRF cavities. We know that quenching is an important failure mechanism for cavities, limiting the maximum field we can reach with them. And these are caused by regions of local heating. But what causes this? Maybe a defect, such as a grain boundary, which may cede the entry of magnetic vortices, leading to heating. We measure this using a bunch of temperature sensors around the cavity, as shown in the figure. We call this a temperature mapping system. A few years ago, we got some tantalizing data from one such system. In the plot, in the highlighted portion, you can see that the field was ramped inside the cavity, shown in red, while the temperature of a local spot on the cavity, shown in blue, increases, but in steps. How is that possible? Is that a signature of magnetic vortex entry? I am commissioning a 50 kilohertz temperature camera to find out.
Since the invention of the first electron microscope, the resolving power has been increasing steadily, and in modern electron microscopes, the resolution is aberration limited. Conventional correction methods using usual detectors are based on collection of many beam tilt series, and in general, those methods require more than 40 scans before the aberration can be reliably measured. On the other hand, the pixel array detector generates 4-dimensional dataset and captures the electron flux scattered to each angle in the diffraction plane. So in just one scan, we can acquire micrographs from various beam tilts. The aberration function can then be calculated as the shift of each image at particular tilt angle corresponds to the gradient of the aberration function. Electron microscope is a linear electron beam accelerator, and in this system, we can measure and diagnose the transverse emittance as a function of the aberration gradient. By tuning the aberration function, this allows us to control emittance growth and hence minimize the loss of brightness of the electron beam.
This is Eric Krupp, PhD student in physics at UCLA. If I say anything that piques your interest, or if you have any questions, please feel free to contact me at the email address listed on your screen. My work pertains to improving beam brightness and stability in electron accelerators. At the Pegasus beamline, I have implemented the round-to-flat beam transform. This transformation produces high 2D beam brightness, which corresponds to one spatial dimension. It also improves the brightness scaling with MTE, which complements CBB photocathode work. The optimization of the flat beam transform can be challenging. CBB affiliates at SLAC and I optimized the flat beam transform using various machine learning models and compared them. At the high-res beamline, at Lawrence Berkeley National Lab, I study the longitudinal and transverse beam dynamics in the dogleg in the hope of reducing time of arrival jitter and improving stability. In addition, the use of a machine learning virtual diagnostic is planned in order to reduce this jitter in post-processing. Thank you.
Hi, my name is Will DeBenedetti, and my research focuses on protecting photocathodes with two-dimensional materials. Photocathodes transform light into electricity using the photoelectric effect. The materials traditionally used to grow photocathodes are easily oxidized. They must be grown and stored under the most pristine vacuum conditions. In my research, I use two-dimensional materials such as graphene and boron nitride to encapsulate photocathodes that acts as an impenetrable barrier to atmospheric contaminants that oxidize and poison photocathode performance. The success of this research will enable rugged, air-stable, high-efficiency photocathodes to be grown at Cornell University in Ithaca, New York, and shipped to the University of California at Los Angeles for our collaborators to use in a photo-injecting device. Thank you very much for your attention, and I look forward to meeting you at my poster.
Optical stochastic cooling is a beam cooling technique which uses a pair of undulators to compress the phase space of the beam. Infrared light is produced in the pickup undulator and is then amplified and reintroduced in the kicker, where it provides a corrective kick proportional to the deviation of each particle's momentum. At NIU, we are working to produce a particle tracking simulation of OSC at IOTA using Elegant. We are developing two elements in Elegant to simulate the effects of the two undulators. This will model the full IOTA ring, which will allow us to study the behavior of OSC more closely. We are also interested in the effect of amplifying the radiation produced in the pickup undulator. This is called active optical stochastic cooling, which has the potential to produce significantly faster cooling times, so we are testing a simple laser amplification scheme at Argon's APS light source.
Energy spread is an important figure of merit for electron beams. New applications become possible when energy spread is reduced from hundreds to single milli-electron volts, including vibrational spectroscopy. The state-of-the-art method for reducing energy spread is shown on the left in panel 1. A magnetic field disperses the beam, and an aperture selects out the energy range of interest. Current must be lost, making detection of the beam more challenging. In our design, shown in panel 1 on the right, a laser synchronizes electron emission with oscillating cavity fields. Two cavities equalize electron energies without loss of current. Panel 2 shows the results of simulating our design. Blue curves show the initial beam, red the final beam. The initial beam has a full width at half maximum of 1 electron volt, the final beam 5 milli-electron volts, a factor 200 reduction. The simulations incorporate a realistic model of experimental noise, as shown in the inset on the bottom figure. These results are encouraging us to move forward with an experimental implementation of our design.
This is Ken at Arizona State University. We're under quarantine right now, but I got exciting news to share. We got prospects on lower emittance measurements using the ASU cryo-cooled electron. This gun has universal cathode compatibility because we use the Omicron paddle cathode holder, which is standard in a plethora of surface diagnostic tools. Not to mention, it's going to be completely connected under vacuum to a cathode growth chamber, allowing for in situ beam brightness measurements. Plus, we got cryo-cooling system, bring it down to the 20 Kelvin and below, and that lets us take to the next level of low emittance. So, you want to find out more? We got a joint meeting with UCLA's Eric Kropp and Cornell's William Lee. I don't got much time. Come on down to the poster. Experiments on low emittance beam generation. I'll see you there.
Hi everyone, my name's Matt, and I'm going to give you a quick look into point-to-point space charge and high-brightness photoelectron beamlines for ultrafast electron diffraction. In the design and operation of accelerators, simulations are often used. Electron interactions in these simulations are often approximated because the full calculation of these interactions would take far too long. For very cold, dense electron beams, however, the standard approximation used in these simulations fails. Because the CVB aims to make very cold, dense electron beams, it's important that we are able to simulate the dynamics of these beams properly, and that's what I'm aiming to do. What I've found is that compared to the standard approximation, more realistically, the emittance of these beams is actually larger by a factor of 2 to 3, and the other metrics such as the core emittance are actually larger by a factor of 3 to 5. If you want to know more about my research, come talk with me separately. Thank you.
Particle accelerators are complicated. They take a lot of people power, time, and knowledge to control and operate. Most user facilities rely heavily on very slow parameter scans and a lot of human brain power to change machine settings for different user needs, which is expensive and results in a lot of unusable downtime. To improve the control and tuning of particle accelerators, scientists at SLAC National Accelerator Lab are exploring using neural network-based surrogate models to aid in finding optimal machine settings quickly and reliably, thus reducing wasted time and saving money. With funding from the DOE SCGSR program, I have been working at SLAC to study how surrogate models can be used for optimization in order to allow for online machine tuning. Hopefully, machine learning methods will be applied to more accelerator systems to help us better control and use particle accelerators for novel science research. For more information, please feel free to email me. Thanks.
Hello everyone. My name is Ajinkya Hire and I am a graduate student in the RHIC group at the University of Florida. As you all know, niobium 310 coating can be used inside a SRF cavity to increase its performance. But is there any other material that can be used instead of niobium 310? How about using its brother niobium 3 germanium, the highest critical temperature record holder till 1986? Can we use it instead of niobium 310? Before coating the SRF cavity with niobium 3 germanium, we first need to understand its thermodynamic stability. So how thermodynamically stable is niobium 3 germanium? With my research, I'm trying to answer this exact question. To understand the thermodynamic stability, I'm using cluster expansion and semi-grand canonical Monte Carlo calculations to calculate the free energy curves for niobium 3 germanium. To know more about my work, please visit virtually our poster presentation on alternative materials for beam acceleration. Thank you.
I'm Michelle Kelly, and I've been studying grain boundaries in niobium 310 from first principles. Many of the desirable superconducting properties of this material can be attributed to these long conducting chains of niobium atoms in the A15 phase that span the 3 orthogonal directions. And while the effects of point defects have been studied, what's missing is a comprehensive study of how an extended defect, like a grain boundary, impacts the material. And that's where I come in.
I've identified a collection of representative structures consisting of both tilt grain boundaries and twist grain boundaries And from my understanding, I'm the first to do an atomistic calculation of a twist grain boundary in this material.
I don't have enough time to share my results on how grain boundaries affect superconductivity, but they're good, and you could see them at the poster session.
Photoemission is a fundamental process of ultrafast electron and linear particle accelerator applications. One main way to improve upon the performances of these applications is to use brighter electron beams. In order to have a brighter beam, we need the cathode that is emitting these electrons to have a small mean transverse energy. This has led to a lot of emphasis being placed on understanding the photoemission process and minimizing the mean transverse energy from cathodes. My research utilizes a unique energy analyzer that can obtain the 3D energy momentum distributions of photoemitted electrons with energies as low as 1 millielectron volt and with sub-millielectron volt energy resolution. The electrons are emitted from a liquid helium-cooled cathode, which is necessary to obtain the lowest possible mean transverse energy. This makes it an ideal device for studying nonlinear and near-threshold photoemission, which gives us better insight into what is increasing the mean transverse energy of the cathode. This energy analyzer was previously used at Berkeley on a copper 100 cathode that was cooled to 30 Kelvin with liquid helium to measure a mean transverse energy of 5 millielectron volts, which is a record low mean transverse energy.
Hi there. My name is Michiko, and I'm a graduate student at the University of Chicago. My research is in the area of beam dynamics, specifically nonlinear integrable optics. This is a novel concept to deal with something called fast collective coherent instabilities, which oftentimes limit peak beam intensities achievable by machines such as RHIC. Current mitigation strategies all have significant disadvantages, especially as it relates to the dynamic aperture size. However, integrable optics avoids these problems. My recent research has been in the experimental implementation and optimization of these integrable optic systems at the IOTA ring at Fermilab. So for this session, I have two posters. One is an advanced optics category, and it presents our very exciting results from run 2. And the second poster is in the machine learning category and presents our efforts at circuit modeling and online beam-based diagnostics for integrable lattices. Thank you, and I hope to see you there.
My name is Gerard Lawler. I'm a graduate student in physics at the University of California, Los Angeles. I'll be presenting progress in an area increasingly emphasized by the CBB, nanostructured cathodes. Nanoscale tips, perhaps the most well-known, are ubiquitous in low-charge, low-emittance applications such as electron microscopy. They operate on the principle of field emission rather than thermionic or photoemission, and so represent a unique set of challenges and advantages. Significant progress has been made with respect to increasing their charge operation by using arrays of emitters. Gating these arrays for use in radio frequency environments is thus promising for high-charge, low-emittance applications. As depicted in the figure to the left, I'll present the next step in emitter geometry, the nanoblade. It can be thought of as an extruded nanotip, and so offers all the advantage with significant improvements in robustness, especially with respect to high laser fluence. I'll detail the manufacturer, initial emission studies, and considerations of plasmonic enhancement of emission and use in high-gradient photoinjection.
Optical stochastic cooling is a particle beam cooling technique which involves a particle emitting a wave packet in an undulator and interacting with the same wave packet in another undulator downstream. The wave packet is amplified between the two undulators, ultimately resulting in an energy kick given to the particle. The Caesar test will include a titanium sapphire crystal optical amplifier, which functions by creating a population inversion inside the crystal. This is achieved by using a pump laser to transfer energy to the crystal via a 4 energy level pumping scheme shown here. From them, you can derive equations describing the intensity change of the two beams through the crystal. I've been working on implementing this setup in the synchrotron radiation workshop so that parameters unaccounted for in the analytical model may be analyzed and optimized. When considering Gaussian pulses, these include the focus location and waste radius of both beams. Shown here are two such gain optimizations for a model that ignores saturation effects. A working model that includes saturation effects is in development now, with the ultimate goal of testing the model with undulator radiation.
Hi, I'm William Lee from the Maxim Group at Cornell University, working on ultrafast electron diffraction. Ultrafast electron diffraction requires high-quality electron beams, in other words, beams with low emittance, to achieve high spatial resolution. The emittance of the beam at the sample is ultimately limited by the emittance at the source, and as the boxed equation shows, this emittance is linearly dependent on the laser spot size and is dependent on the square root of MTE. Optimized simulations have shown that the spot size needs to be on the order of just a few microns to get the emittance we want. This is difficult to achieve with standard cathode designs, as the final focusing lens normally needs to be outside of the gun, causing the minimum focal length to be on the order of centimeters. By designing a cathode with a lens built into the back of it, we can reduce the focal length down to the millimeter level, and thus enable the laser to reach a tighter focus. With this new cathode design, we were able to measure an emittance of less than 5 nanometers at the sample, seen in this phase space on the right, and are continuing to push this number further down, hopefully all the way to the single nanometer level. For more details, please see my poster.
Hello everyone, my name is Joshua Mann and I am a graduate student from UCLA. My research involves simulating electron emissions from field-enhanced nanoblades. To do this, we've run a custom time-dependent Schrödinger equation code, now using the operator splitting Fourier method, with a Jellium slab potential and fields calculated using the finite difference time domain via numerical. One result that I'll discuss during the poster session is the deviation from the frequently quoted 10 UP, or 10 times the power mode of energy, classical cutoff, and the new classical simulations performed to get these new constants. Additionally, to address the experiment's finding was likely space charge limited current from these cathodes, we begin running quantum simulations with the Coulomb interaction, treating electrons effectively as planar within the metal and cylindrical outside the metal. So please stop by our breakout room. Our poster is titled Nanostructured Photocathodes. Thank you and enjoy the rest of the session.
Hi, I'm Kevin, and I work with Tomas Arias. My research is ambidextrous photoemission studies to help searching for next-generation ultra-high brightness electron sources. Collaborating with others in the beam production team, I have developed ambidextrous framework to calculate mean transverse energy and quantum efficiency of single crystal photocathodes, and also studied ambidextrous coherent two-photon processes and how they affect the photocathode performance for applications requiring intense laser illumination. I have also identified some stable crystal structures of alkali antimonides, a class of promising photocathode materials that are not yet very well understood. Lastly, we are developing a more advanced ambidextrous framework to calculate NTE and QE of more complex photocathodes, such as those that are capped with 2D materials for air stability, which are of great interest to CBB in the future.
I work on exploring materials other than niobium and niobium tin for SRF applications. The materials we are interested in are those that could theoretically increase the maximum accelerating gradient of a cavity and improve the operating efficiency. The conventional choices for materials deemed suitable for this purpose are not exactly new. Many of them have been studied in detail already. The RF measurements produced from these studies have always been extremely underwhelming when compared to both theoretical expectations and the capabilities of niobium. To me, the question of alternative materials then becomes, why is it these materials are underperforming? Is there something we can do about it? Or is it an intrinsic issue that has not yet come to light? With the combined expertise of the Center for Bright Beams, we've been attacking these questions from a number of directions and disciplines. A summary of our progress is presented in the poster on alternative materials for beam acceleration.
One of the biggest barriers between identifying a crystal with useful properties and integrating it with known technology is growing high-quality films of said material. When grown, thin films tend to have some amount of incompatibility with the substrate, potentially leading to the generation of undesirable defects. Further, it increases the difficulty of optimizing the growth conditions of the crystal, further increasing the time between identifying the material and integrating the technology. To help optimize these conditions and decrease defect concentration in grown photocathodes, we developed an algorithm which computationally cleaves surfaces from periodic crystals. We applied this algorithm to the materials product database and focused efforts on identifying low-energy surfaces. We then structurally optimized these surfaces and identified thousands of substrates with comparable work of adhesion to currently used substrate materials. We then tactically matched cesium antimonide to this computational database of substrates to identify alternative surfaces to grow the photocathode on.
Alkali antimonide photocathodes are used in low-gradient accelerators as a source for high-quality electron beams. As of now, we don't have a detailed understanding of how alkali antimonides would perform in the high extraction fields of high-gradient accelerators. This is mainly because the less than ideal vacuum conditions that high-gradient accelerators are known for would lead to a quick decline in alkali antimonide cathode performance. However, combining state-of-the-art photocathodes, such as alkali antimonides, with a high-performance RF photoinjector would be a recipe for higher brightness electron beams. Beams of this quality would, in principle, offer advancements in applications such as ultra-fast electron microscopy. So the aims of this project are twofold. One is to design and employ a compact vacuum suitcase, a transfer chamber that could take the cathodes from their growth facility to a facility with a high gradient accelerator. The second is to characterize the performance of alkali antimonides at high extraction fields. Come to my poster session to hear more about the results from our first test transfer of alkali antimonide photocathodes in a high gradient accelerator.
Hi, I'm Chris Pierce, and I studied the role photocathodes play in determining beam brightness. Reducing the mean transverse energy of photocathodes is a promising route to brighter beams. However, nonlinear space charge forces can distort phase space and dilute beam emittance as seen in the figure to the right. This poses a challenge to seeing the improvements offered by photocathodes at the point where the beam is used. In my group's poster, we examined the maximum performance of 3 hypothetical beamlines. These were inspired by contemporary space charge limited applications. We show that for bunch charges that matter to users, photocathode MTE improvements down to the level of 1 millielectron volt still matter. This scale of photocathode MTE would provide a 2 orders of magnitude increase in the brightness of existing photoinjectors. If you're interested in learning more, then please stop by our virtual poster tomorrow.
Hi, my name is Ryan Porter, and the major topic I've been working on with the Center for Bright Beams is improving the accelerate gradients of niobium 310 accelerator cavities. For a short summary, this work can be divided into 3 main parts, each of which spans many people in the center. First, we've been studying why our cavities stop functioning using experimental data, surface microscopy, and theoretical models. Our main takeaway from this year is that reducing the surface roughness of our niobium 310 is the best route to improvement. How can we get smoother niobium 310? The best option is to grow it smoother. We've been studying niobium 310 growth, and our conclusion is the surface roughness is largely caused by poor uniformity of the initial tin coating. Using our knowledge of niobium 310 growth, we modified our growth process and successfully created smoother niobium 310 on our first try. We've also developed a technique to electroplate tin onto niobium, creating a very uniform tin layer to start our growth from and creating even smoother niobium 310. Thank you.
Hello everyone, my name is Pallavi and I'm a graduate student at ASU working with Siddharth Karkare. My project is based on epitaxial growth of alkali antimonide photocathodes and measurement of their optoelectronic properties to begin with. So a lot of work has been going on these materials for decades now, but unfortunately there has been little or no understanding of their optoelectronic properties like band gap, electron affinity, etc. So we're trying to develop some setups for the measurement of those properties, and these measurements include photoluminescence and photoconductivity. So we are going to talk about more that in our poster. So if you're interested, please stop by our poster. Thank you.
I'm Nathan, and I study the properties of niobium and niobium 310 SRF cavities using first principles computational methods. Calculations for defect formation energies, interaction energies, and hopping barriers, like these barriers calculated by our undergraduate researcher Sam, help us understand how the material is changing during the different stages of cavity preparation. Electronic structure calculations help us link changes in material composition to changes in key properties, like superconducting transition temperature and electron scattering times. Here are some plots I produced with my coworker Michelle showing which electronic states on the niobium Fermi surface experience more intense or less intense scattering. I used these results in collaboration with other CBB researchers to develop new cavity preparation recipes and to improve our understanding of SRF physics. To find out more about my work, visit my posters.
Inhomogeneities in niobium 310 films contribute to energy losses in SRF cavities. While it is well known that a surface oxide is present during niobium 310 film growth, the behavior of this surface oxide and tin during tin deposition procedures is unknown. An understanding of this surface oxide that interacts with tin is critical to understanding the niobium 310 film growth process, and growth models must take this into account. I have shown with helium atom scattering for the first time that the surface oxide forms a well-ordered 3x1 oxide surface structure on the niobium 100 surface up to 1128 Kelvin. This determination of surface structure and chemical composition at temperatures of tin deposition provides unique insight into niobium 310 film growth. This newly revealed stability of the 3x1 oxide makes it a proper model surface to study tin mobility and alloy growth in future studies.
The efficiency of niobium 310-coated SRF cavities is limited by the presence of surface defects within the first micron of the cavity surface. However, the fundamental growth mechanisms that dictate niobium tin alloying during the standard vapor deposition process are not yet known. As surface chemists, we're examining the role of niobium's native surface oxide layer in tin coordination and mobility during the initial absorption, lateral diffusion, and alloying process. Answering these questions will ultimately help us understand how atomic scale defects and deposition conditions impact the homogeneity of formed grains. We've built an ultra-high vacuum chamber to prepare and analyze tin alloying in situ, which enables both topographical and electronic surface characterization. Using an electron beam evaporator on an oxidized niobium single crystal surface permits sub-monolayer atomic scale resolution imaging. So to summarize, we hope to optimize niobium cavity coating procedures by studying niobium-3 tin growth.
Well done, everyone.
So this afternoon we'll have two talks in this session. The first one is by Gennady Stupakov, and he's going to talk about cooling in colliders. So let me introduce Gennady. Gennady is a senior scientist at SLAC. He received his PhD from Budker Institute in Novosibirsk in 1979 on plasma physics research. In 91, he moved to the US to join the superconducting super collider laboratory in Texas, and later joined SLAC in 94. At SLAC, Gennady worked on a variety of topics, including beam impedance and instabilities, free electron lasers, plasma wake field acceleration, and other collective effect in relativistic beams. Most recently, Gennady has been involved in the development of the coherent electron cooling scheme for Hadron Collider. And Gennady was elected an IPS fellow in 2005. In 2019, he was awarded the International FEL Prize for his invention of the echo-enabled harmonic generation, which is the FEL seeding techniques. And likewise, Gennady is a frequent teacher at the US Particle Accelerator School, and he notably co-authored together with Greg Penn a textbook on classical mechanics and electromagnetism in accelerator physics, which was published in 2018. So Gennady, thank you for agreeing to talk about cooling, and please take it from here.
Okay, thank you, Philippe, for the introduction. And let me switch to Keynote. Keynote.
Okay, good to see you, Oscar.
All right, you see my full screen?
Yes.
Okay, good. So it's a pleasure and honor for me to talk on this subject. Thank you, organizers, for inviting me. And the outline of my talk is here. I will start with a brief introduction. I will talk about sort of classical methods of cooling, which are stochastic cooling, electron cooling. And then in the second part, I will talk about more modern methods, coherent electron cooling, optical stochastic cooling. I want to say that my emphasis in this talk is a focus on conceptual ideas, basic physics. I will not go into technical details. And for those who are interested and would like to learn more about cooling, I highly recommend find talks by Sergei Nagaitsev from Fermilab. I have a couple of references here. And he is also giving a US Pass course on cooling in 2021, if of course it's not moved to a later time because of the pandemic. Starting with an introduction, I am asking this question: why do we need beam cooling in colliders? And I start with this formula for the luminosity, and you already saw it in Frank Zimmermann's presentation. You collide beams with particles N1 and 2 in these beams with the repetition rate given by F0. And the luminosity is given by this formula, and these are transverse dimensions of your beams. You want to have larger luminosity, you need smaller transverse dimensions. And as you know, you do this with a smaller beta function, but also you need a smaller transverse admittances. So that's why we want to control these admittances and to make them smaller. But that's not the only thing. You also want to control beam energy spread because that defines your bunch lengths, and that's also important for collisions. So overall, you want to control all three quantities here, and in your machine, in a collider, you have processes which are trying to increase them, and they are listed here, some of them, scattering. And that includes intra-beam scattering, that's collision between the particle and the same beam, or beam-beam collisions, or collisions with the radio gas and maybe something else. If you inject your beam in the ring, not exactly on the orbit, there is a mismatch, the beam decoheres, and that will increase your emittance. Wake fields will act on your beam, and as well as space charge. So with all these, as well as some other factors, we conclude that we often need to have beam cooling in both transverse directions in general and in the longitudinal direction. What is not cooling actually? It's good to think what we do not cooling. Beam scraping. If you put in collimators in the machine, you remove particles with large betatron amplitudes, and that would lower your emittance, but at the same time you lose particles. You don't want to do that. We don't call this cooling. Cooling due acceleration. When you accelerate your particles, the transverse emittance goes down, but we don't call this cooling because we are talking about the normalized emittance, which remains constant during the acceleration. If you transverse your beam, if you expand your beam in transverse direction, that would lower its transverse temperature. If you go into the beam frame and define the temperature, it would go down, but the emittance doesn't change, of course, so that's not cooling. Finally, I want to mention some fancy scheme which involves emittance exchange. You can arrange your beam line in some tricky way so that you can exchange, say, a longitudinal emittance with a transverse one. That can drastically change your emittance, and that might be useful for several applications. Still, we don't call this cooling. In six-dimensional phase space, the six-dimensional emittance doesn't change in this exercise. So that's not cooling. Now, let's say a few words about cooling by synchrotron radiation. If we are talking about electron or positron circular machines, then there is a strong natural cooling mechanism in this machine due to the incoherent synchrotron radiation, with a typical cooling time which may be 10, 20 or milliseconds or somewhere in that range. And the beam is cooled due to this radiation to some level, which is defined finally by a recoil in the process of radiation, what's called quantum diffusion. And this naturally cools the longitudinal degree of freedom, but through the coupling in the dispersion regions, it also cools your horizontal beam, again to the level which is defined by the quantum fluctuations. Anyway, this process is we do have a very strong cooling mechanism here. So we are not so much concerned about the cooling of electrons, positrons, and circular accelerators. In contrast, hadrons radiate much less due to their large mass. They start to radiate noticeably, and Frank Zimmermann talked about that, when you go to very high energies. And then the synchrotron damping time starts to play some role. As an example, for the LHC at 7 TeV proton beams, the cooling time due to the synchrotron radiation will be 1 day. But if you go to the future collider, future circular collider FCC at 60 TeV protons, then the damping time goes down to 2 seconds. Then it's an important part of your dynamics. But if you are not there, so you don't have this, if you're not at these high energies, you need some other mechanism for the cooling. And people invented this mechanism in the past. And now I go through some of them, starting with the stochastic cooling proposed by Simon van der Meer and CERN in 1969. It was a crucial technique for accumulation of antiprotons in the discovery of W and Z bosons. And that's why van der Meer with Carl Rubia received Nobel Prize in physics in 1984. To explain you the basic physical mechanism of this cooling, I have a simple simulation here, an animation, which can be easily done by everybody who can write a simple MATLAB code in few lines. And what it does here, I have this circular machine. This is my ring. I have a beam, which in this case consists of 10 particles. And I have a pickup here, which measured offset of my beam at this location. And then it sends a signal through some amplifier G, and I apply it at this location to the particle when it arrives here. And you see I have some spread in the betatron oscillations, which means that I have my emittance. So what's important in this case is that you locate your kicker downstream of your pickup at a distance which is 1/4 betatron wavelengths plus any integer number. And then you apply your kick, you change the direction, the angle of your particles in proportion to the signal from the pickup multiplied by this factor G. So let's see what happens in this case. And I show you 3 turns. My beam makes 3 revolutions in the ring. And you probably start noticing that the amplitudes of the betatron oscillation goes down, and eventually after 3 turns, when it stops, you will see that all my particles basically are sitting on the reference of it. I cooled my beam, the impedance went down very much. Well, of course, this is a toy problem. In reality, as I say here, the pickup and the kicker interact, of course, with many particles. You don't have 10 particles, you have 10 to the 9ths or 10ths or 11ths in your beam. So a more real model, a more realistic model is shown here. Basically, you have your ring, which is a squarish here. That's your beam goes in the direction. Your pickup now, of course, measured the signal from many particles, which is shown here. But then the rest is the same. You send your signal through an amplifier, and there is a kicker here, and you apply it downstream, 1/4 of a plasma betatron wavelengths plus some integer number. Turns out, if you go through the theory of this, you find out that the cooling rate in this case, and this simple model can be calculated. It's shown here. The cooling rate is the inverse cooling time, given by the simple formula 1/2. This is the revolution period T, and then this n sample. That's some number of particles which are sampled in your system. In my trivial examples on the previous slide, I had it equal to 1. Basically, I sampled every particles, and then the cooling time becomes a few revolution periods, as you saw in that simulation. In reality, for the coasting beam, for example, n sample is the number of particles in the duration of the kicker, which can be estimated here, and the duration of this kick can be written as the inverse bandwidth of your amplifier. So that's a crucial number here. And for conventional stochastic cooling, which uses RF frequencies, this is typically a few gigahertz. Then you immediately conclude that if you want to do faster cooling, you need a broader bandwidth. And we'll talk about that in the second part of this presentation. And I have a reference here with all details. There is a book by Dieter Möll shown here. If you want to learn more and how this formula is derived, you can look at that book. An example of practical application of stochastic cooling is RHIC, where the stochastic cooling was used to cool down uranium and gold ions. And I have a reference here with Mike Blaskowitz, the leading author on this work. And they achieved three-dimensional cooling, again, in this range of frequencies, which increased their luminosity 5 times for uranium and 4 times for gold-gold collision. This is a picture from one of these works, which shows this trace here. This is a simulation without cooling. If you don't do nothing, you inject your beams, and because of the interbeam scattering, the luminosity goes down. Notice the scale here, these are hours, so it's a very slow process. But if you add the cooling, there is a measurement by the Phoenix detector, and pretty close to its simulations, where you increase your luminosity and then much slower decay here. As I mentioned, the traditional microwave stochastic cooling in the range of few gigahertz, and it may be adequate to in the electron-ion collider for electron-ion collisions, because usually people don't have many ions in the bunches at the level of 10 to the 9th, but they also want to collide electrons with protons, and they would have much larger number of particles in the bunch, and then turns out that becomes very slow. And I like this nice picture, which I believe Michiko also showed a part of it. It's important when you amplify your signal and send it ahead of the bunch, since the bunch's particles are pretty much relativistic, you have to go on a shortcut. So they send it through a straight line while the particles are traveling along an arc of the ring. And that shows they had a microwave link when this antenna sends signals to this antenna here, which is also shown here. And that's why you make sure that your signal arrives before your beam goes there. Okay, so that was all about the stochastic cooling. And the second mechanism is the electron cooling in relativistic beams. It was invented by Gerd Butker at the Institute of Nuclear Physics in Novosibirsk in 1966. It was tested there, where they built a small proton ring at 68 MeV protons. And they showed experimentally that it works. And according to Sergei Nagaitsev, who is a world expert in this field, since 1974, now about 20 electron coolers operate in the world. What the physical idea behind this cooling? It's basically very simple. In your ring, you select a section, a straight section, and you have your ions or hadrons traveling here, and they are relatively hot. And what you do, you would generate an electron beam with electron gun, send it through this region where they go together with the ions. And what you do actually, you mix a hot fluid of the ion beam with a cold fluid of the electron beam. And due to this mixing and interaction between them, they try to equalize their temperature. And then you dump your electron beam, which is a little bit heated up. And you keep repeating these many revolution periods and slowly cool down your ions. Well, that's a very sort of trivial and naive explanation. If you want to be a little bit more scientific, you have to look what exactly happens in this interaction of the electrons and ions in this cooling region. And first thing you realize that for the effective interaction, they should collide with each other. These are just Coulomb collisions, which I illustrate here in this picture. This is, say, an ion. This is an electron. When they collide, that creates some friction force. But we know that these collisions only become effective when the relative velocity of these particles is very small. So the first and the most important requirement, you want to have your electron velocity or gamma factor equal to the hadron velocity. And then if you go through some plasma textbooks, you can work out a formula for this friction force. And this is the force for an ion in the beam frame when it moves through this electron fluid. And I make a plot here of this force, which has this shape. If an ion is moving through this electron fluid with a velocity which is larger than nominal velocity, it has a negative friction acting on it. It will slow down and goes to here. And if it's moving with a velocity slower, then it will be accelerated by this positive friction force. So that's the mechanism now for this cooling. And with this formula, you can start doing practical calculations and actually go and start doing design of this machine. In reality, of course, the situation is much more complicated than what I showed you on these cartoons. I show you here the electron cooling at FNAL recycler, which worked there since 2005 to 2011. And that was the highest energy electron cooling with the electron energy 4.3 MeV. And from the quality of the gamma factor, you would conclude that corresponds to 8 GeV, in this case, antiprotons. And what you see here on this cartoon, that's how the whole thing works. You have this electron accelerator here, and that's shown here where you have the gun, and the gun generates electrons. You send them here, they go in this direction, and then in this region, they combine, they go together with the antiprotons, that the antiproton beam line. That's about 20 meters as shown here. They cool down a little bit in one passage. Then you return your electrons. You just don't dump it as was shown on my simple cartoon 2 slides ago. You want to send them back and bring it here. So then when you collect these electrons, you don't dump their whole energy. You have some energy recovery scheme. And with this recovery scheme, they were able to do 0.5 ampere DC beam current. Your electron current runs all the time here. It was optimized for primarily the longitudinal momentum spread here. Again, there is a reference here with Sergei Nagaitsev as the first author in PRL, which documents this remarkable achievement of this scheme. And also a more sort of the latest development and very interesting one of this electron cooling, example of this cooling is has been done quite recently at RHIC, and the cooling device is called low energy RHIC electron cooler, or LRIC. The interesting technology that they used here, they went, instead of DC electron current, which was on the previous slide, RF-based electron beam that they generated bunches here, and then they would accelerate them. And there is a lot of doing a lot of gymnastic with the beam in order to keep it small energy spread, which is very important here. And another complexity was then, and then they go into the beam line of the yellow ring. They combine them with, in this case, they were cooling gold ions, and they and in this region they go, electrons go with the electrons. They cool ions a little bit, and then they make a turnaround 180 degrees, go in the backward direction, and now they go together with these ions in the other ring, which is the blue ring. And only after that they damp this electron. So it's a pretty complicated machine, and it worked very well. And just recently this year there is a publication shown here where this is all described. Now I'm looking at my watch and looks like I'm a little bit slow. That's a picture of this LRIC in the tunnel, and that's their results. I probably have to start skipping something and go faster. So let me say a few words about the challenge of cooling in electron-ion collider. The design of the electron-ion collider, if they want to go to the maximum luminosity, requires cooling of protons at 100-300 GeV with a cooling time about 1 hour. And traditionally, DC electron cooling schemes are not scalable very well above 10 GeV. You saw at Fermilab they did it at 8 GeV. And conventional stochastic cooling is also very slow for bunch protons, too many particles in each bunch. So over the last decade or so, several new concepts of ion cooling were proposed, which have a promise of much faster cooling rate. What they use what's called coherent electron cooling, and I want to spend a few minutes now going to the coherent electron cooling. Again, the inventor here is Yaroslav Derbenov, who a long time ago in 1980 published a paper under the name Enhancement of Electron Cooling Through Intrinsic Instability of the Electron Beam. That's not a good name for a fancy new scheme. So that's a picture from his paper, 1980. And if you look at it, you recognize that that looks like the traditional electron cooling. There are ion beam, there is electron cooling, except for they interact here, then they are separated and they interact here again. At about 2009, Vladimir Litvinenko and Derbenov revived the scheme under the name of coherent electron cooling. That's a much better name. And I want to explain you the physics behind this cooling in this picture of the conceptual generic, some generic coherent electron cooling. You see the picture from the previous slide. I have my ions, I have electrons. And if you look at an ion which interacts with electron here, it interacts with it decelerates electrons which are ahead of it, and accelerates electrons which are behind them. It attracts them. Then you separate these two beams. Ions go through one chicane here, which has R56, that's a 5-6 element of the transport matrix, and electrons go through this region. It has another R56. Since electrons are shifted depending on their energy, it turns out that this energy perturbation creates in the electron beam a tiny density perturbation of the electrons. And then when you combine this electron and ion, which we call kicker, this is called the modulator, you will find out that this density suppression here creates an electrostatic field of this profile. And meantime, ions, due to this R56, fast ions are going ahead, slower ions are delayed and they are behind. And these fast ions go into the deceleration phase, this is to the acceleration phase. And that's how you move them toward the center. That's cooling. That's the concept of this cooling. And this slide just repeats what I just said. You do it over many passages and decrease the energy spread in the 100 beam slowly over many revolution periods. When you start doing this kind of analysis, it's always useful to make a simple theoretical model. And I show you a formula which I derived relatively recently for this generic coherent electron cooling for the inverse cooling time or the cooling rate, just to illustrate what's involved in this process. First of all, it's scaled like 1 over gamma cubed. You cannot go too far in energy. This is well suppressing. It's inversely proportional to the energy spread in your hadron beam and inversely proportional to the energy spread in your electron beam. You want to have it small. It's proportional to the charge in the electron beam. You want to have it large. And it's also proportional to the length of the modulator and the kicker, but there are limits how long you can make. If you use this formula and you substitute some reasonable parameters for electron-ion collider, you find out that this will be too slow cooling for the electron-ion collider. So actually people realized it right away in the original Litvinenko-Derbenov proposal, and you already saw Michiko showed you the scheme. You supplement this, what I call generic coherent cooling with some kind of amplification. In this scheme that was proposed to be a high gain free electron laser. So yes, amplify your signal here. And then when particles go to the kicker, then you will see a faster cooling rate. This scheme actually by Litvinenko's group They spent quite a large effort for many years trying to experimentally demonstrate it, and that's the scheme of the setup, and that's the picture what they did. Unfortunately, they were not able to do that, and that shows that these cooling experimental schema are really challenging. What they found, there was too much noise in the electron beam. But they turned it around and they said, we understand the origin of this noise, some kind of instability, which they called plasma cascade instability, PCI. And they said, oh, we now can use this instability and we will invent a new cooling technique which doesn't use the free electron laser. It just amplifies the signal in the electron beam. And you see here, this is the modulator, and the blue thing is the electron beam. And you just focus and defocus it with solenoids. And turns out that creates an instability and amplification. So now, again, Michiko talked about that. They are trying to demonstrate this experimentally. This is a picture, and these are the solenoids which are installed at RHIC, and hopefully they will be able to demonstrate it. I have a reference here where the scheme is presented and explained. And another approach was proposed that actually earlier than this PCI instability by Daniel Ratner from SLAC, who noticed that you can actually have another amplification scheme, which in my original cartoon, if you remember it, I had just this chicane in the electron path, but now you add just a drift equal to 1/4 of plasma wavelengths. If you create a density perturbation in the beam and let it propagate in a drift, it starts to oscillate longitudinally with the plasma frequency. You need 1/4 of this plasma wavelengths. And then another chicane. Turns out if you do that, you amplify your initial perturbation. You can have stronger kick here, faster cooling time, or you can do 2 amplification cascades here. This is called microbunch electron cooling. It's now started as a possibility for strong cooling in the electron ion collider at RHIC. I have here parameters of this system. I probably don't have time to go over them, and let me spend a few more minutes on my last scheme, which I wanted to explain, optical stochastic cooling, invented by these people, Zolotaryov, Mikhailichenko, Cholens, in 2 publications at the beginning of 90s. And the idea is relatively simple. They say we want to raise very much the frequency of the stochastic cooling. If you remember, the cooling rate is inversely proportional to the bandwidth of your amplifier. So instead of using a pickup, that was Max Zolotarev's idea, they want to use just a wiggler or undulator. This is a system where you have an oscillating magnetic field, and when the beam goes through the thing, it oscillates. That's the trajectory of your electron. And when you go through here, it radiates electromagnetic radiation with this frequency, where gamma is the gamma factor. This is the undulator parameter, and this is the involved the period of your undulator. So the longitudinal position of the particle when it does that is encoded in the phase of its radiation. That's the information which you take. You can take the signal, amplify it, and then you need a kicker. And the kicker is a similar wiggler. You send this pulse, which is here amplified, and when it propagates with the electron, it will change the particle's energy, and the change again depends on the phase. That's how they play the game. And they raise the stochastic cooling frequency from several gigahertz, as I mentioned earlier, to, if it's a wavelength 1 micron, it will be raising in 3 times to the 5th gigahertz, which is many orders of magnitude larger. You probably saw this picture already. That's I took it from Jonathan Jarvis' talk. It's a little bit more detailed. That's the pickup undulator. Then you separate your beam, which goes this way, and the electromagnetic signal goes straight. you can amplify it, or you may not amplify it. In the first experiment, they're not going to amplify it, and then it goes to the kicker region, and you combine them with the proper phasing, and that's how you get your kick and cooling. The first proof of principle experiment is being prepared at IOTA ring at Fermilab, at the picture of the ring. I believe this will be in this spot of the ring, and the beam energy 100 MeV. The wavelength is about 1 micron, and they expect cooling time 70-20 inverse seconds. And here I come to my summary, which is traditional cooling techniques, electron cooling, stochastic cooling, have been under active development for several decades now. They are mature technologies used in many places in the world. However, they do not scale very well to high energy gamma 300 and intense beams, electron collider's. And that's why we are actively working on new concepts, and they go under the name of coherent cooling or optical stochastic cooling, and they have a promise of much faster cooling rates. And in the next year or two, we hope to see first proof of principle result from this PCA coherent electron cooling at Brookhaven, and also optical stochastic cooling in IOTA. So this is a very exciting time for the whole cooling community. Thank you very much, and I'm ready to take questions.
Thank you, Gennady. Let's give a round of applause, virtual applause. I think we have time for a few questions. Let me ask, I guess, comment and ask a question. You introduced at the beginning the fact that ultimately the cooling rate depends, when you have an amplifier, depends on the bandwidth of the amplifier. And how does this work for the electron-based technique, the one based on coherent electron cooling or PCA? There you have an FEL, so the bandwidth is limited. And likewise, when you have chicanes, there must be some requirement on, the amplification mechanism to make sure you can amplify information over a very thin slice of the hadron beam.
So I'm sorry, Philip. So what's the question then?
The question is, what is ultimately the bandwidth of the amplification scheme, of the amplification related to the coherent electron cooling and PCA, and how does it compare to stochastic cooling?
Yeah, there is some natural bandwidth in those schemes, and if I can quickly move here, when I try to explain probably too fast, when my ion here in the modulator interacts with the electrons, I plotted this picture of the interaction. So it the length scale, which I do not show here, of this interaction region, that's basically when it divided by the speed of light, that gives you the characteristic time or inverse frequency of the scheme. Turns out this is of the order of the transfer size of the beams in this region divided by the gamma factor. So if we are talking for electron ion collider, we are talking about the beams will have transfer size here, something like 700 microns. Gamma factor is about 300. So we are talking about this region in the length of 2 microns. So that's the divided by the speed of light gives you time of frequency. So that's comparable to the infrared optical stochastic cooling.
Okay.
It's many terahertz, tens of terahertz.
Okay, but when you have an amplifier on the top of these two micropunch electron beams, this changes, yeah?
You mean
like the FEL or the PCA, right?
Yeah. PCA. Both, okay, that's actually a good question. The FEL, as you mentioned, indeed it's a narrowband amplifier. That's one of the disadvantages of this scheme, which was realized, and that's why this one and the microbunch were proposed. Both this PCA and this one, they are broadband amplifiers, so they do not Basically these are the same. Actually, I mentioned it. The effective bandwidth is tens of terahertz, so it's still broadband. It's not like FEL, which has some like 10⁻³ bandwidth of amplification.
Okay, thank you. Let's say, is there any questions from anybody?
Quick question. Is there a limit to how much the microbunching gain should be in, let's say, this coherent electron cooling?
Is there a limit? Is that the question?
Yes.
Yeah, definitely. There is a limit. In principle, and it's related to the noise in that together with a useful signal, which again, I try to illustrate design creates all this and then acts on itself. Of course, you have many neighboring ions which will generate their own signals and they would be kicking your ions. So in addition to the cooling mechanism, which is coherent and repeats on every period, you will have a noise system. So you amplify the noise in the system, and that's what limits your amplification factor. On paper, we can have like 10⁻³ amplification in this, say, 2 amplification sections. We need to lower to about 100 because otherwise the noise is amplified and you start to heat up your beam instead of cooling it. Yes, there is definitely a limit and it's due to the noise.
Thank you.
Okay, let's take one last question maybe, or if there is one. One time, 2 time. Okay, so let's thank again Gennady. Thank you very much. Very nice talk. Okay, good. So our next speaker is Alexander Romanenko. So I don't know if Alex is here. Yeah, he is here.
Yeah, I'm here.
You want to share your screen? I think.
Sure.
Okay, so let me introduce Alexander. So Alexander Romanenko is a senior scientist at Fermilab. He joined the lab in 2009 as a people fellow after receiving his PhD in physics from Cornell University. Alexander currently leads the lab's program in superconducting quantum systems and oversees the lab's quantum technology portfolio. Alexander also serves as associate head for the superconducting radio frequency technology department, which is in the applied physics and superconducting technology division. And he oversees the activity ranging from SRF R&D and work related to projects in this division. His scientific work has been recognized by several national and international awards, including the 2017 US Particle Accelerator Prize for achievement in accelerator physics and technology. He also received one of the 2011 DOE Early Career Award and the 2011 IEEE Past Doctoral Dissertation Award. Alexander is also a fellow of the American Physical Society. So please, Alexander, thank you for coming and take control.
Thank you very much. I think I need to be made the co-host though to be able to share.
This is let's say Joanne is here. Joanne, will you take care? Or?
Yes, I just
took
care of it.
Great.
Thank you very much. Just got it. Yep. Okay, so
you are now. Yeah.
Can you see now?
Yeah, great.
Sorry, I was actually last minute replacement in some sense, so I had to modify slightly the title of my presentation to add a couple of things on the quantum, as you mentioned. Also, in addition to SRF, I'm heavily involved in quantum technology, so I think it could be useful to add a couple of slides to that. But so let me talk about the main subject, which is SRF for colliders. So I'll kind of give a brief highlights of the recent, or in general, about SRF technology and what have happened in the few recent years, and how it applies to modern SRF accelerators and colliders specifically, which are on the horizon. So as I bet most of you know, so the particle acceleration, so the principle of RF particle acceleration as shown here, is when the charged beam is passing through the essentially a resonator, which holds the standing electromagnetic wave, as shown here, and the standing electromagnetic wave, which is changing the direction in sync with the passing beam, provides the acceleration. So to accelerate particles the most over a given distance, you want to have the fields as high as possible, and also preferably you want to have fields on as long as possible. So to enable both of those, so the trick which was implemented starting from 70s and starting from actually Stanford work, is to use actually superconducting cavities, superconducting radio frequency cavities, to take advantage of the extremely high quality factors to actually be able to store these fields to accelerate particles. So so what's shown here, this is a 9-cell SRF cavity, which is a building block of ILC, for example, CLS2. So typically the quality factors of this cavity is extremely high, higher than 10 to 10, and that's the hallmark. So to achieve that, they have to be cooled down to cryogenic temperature, typically about 2 Kelvin. And what that provides, these extremely high quality factors, is actually extraordinarily high efficiency. So the wall dissipation in this cavities to store this field is proportional to the so-called surface resistance, and it's reduced by many orders of magnitude over normal conducting resonators. So, and actually what it leads to, so these cavities are currently among highest quality factors resonators in nature. What we have realized actually over the years, so they also can serve as extremely sensitive detecting devices. And you'll see a little bit on that. And specifically for colliders and accelerators, so it provides affordable continuous wave and long pulse at high gradients. So essentially acceleration can be on all the time. And this is a nice plot, which I think our colleagues from Northwestern University made at some point, which actually show that what I mentioned, that SRF cavity is actually not among the best, but actually the most efficient engineered oscillators in existence, which is quite a remarkable feature. So the only other things is nature given, which is atomic clocks. So and currently, so the range of these quality factors is in between 10 to 11, 10 to 12 for SRF cavities. So and what that leads to eventually also, so you can, with these building blocks, you can build high current, high energy, high brightness beams machines. So and the first figure, so there are several figures of merit, very key parameters which you have to kind of work on and which research focuses on. And so the first one is the gradient. As you're familiar with, this is acceleration per unit length. And this is extremely important for linear accelerators, but also important for all other circular accelerators and so on, because essentially it leads to how long of a building block you have to achieve a given energy of the particles. So the higher the gradient, the shorter the accelerators, essentially. And so one byproduct of that, and it's related to another extremely important figure of merit, quality factor, is that as you increase the gradients via research or advanced surface techniques has been applied in SRF, so you actually turns out that you have to also increase the quality factor, or at least not to let it degrade. So this, because otherwise, eventually, even extremely small, still the dissipated power becomes intolerable. And also the cost of accelerator, which is built using the higher and higher gradients cavities, also scales or depends quite substantially on actually what quality factors do you achieve. So this is one of the analyses which was performed for baseline design for International Linear Collider, and then implementing some of the recent developments, like either using ILC surface processing, which was kind of state of the art up to, let's say, 2012 or so, and then given the progress which we achieved since then, so you can see that you can substantially actually decrease the costs of the ILC machine at higher gradients, and that's via the increase in Qs. So the ILC, which is already mentioned here, this is obviously one of the major applications of SRF, which has been around. The idea has been around already for for quite a while, and hopefully it will be realized. And if it will, it will be the largest SRF installation ever built. So it's 16,000 kVs in 31 kilometers LINAC and so on. So, and Japan is currently considering doing that, as you know. So, and then factor of merit 2, extremely important one, is the quality factor Q. So what it affects, it determines how big of a cryogenic infrastructure, how big of a cryogenic plant you have to operate these SRF accelerators. And so essentially the higher the Q, so the magnitude of the Q directly translates into required the cryo plant capacity. And so it's shown here, so dissipated power, even though it's small, but it's at 2 Kelvin, so it has to be, so the cryo plant has to be able to capture that. And so as you see, so this is the law, essentially, it's inversely proportional to Q. So as you increase the Q, so dissipated power, which has to be handled, correspondingly decreases. And that's a dramatic effect on cost of all CW machines, essentially leading 1, 2, 3, or 4 cryo plants. In this example, for different Q levels, this was the analysis done, I believe, for LCLS2 at the time. And so there was a substantial progress in Q arena, which is nitrogen doping, which many of you have heard or have been involved in also. So this is another extremely important direction. So, and then, so as an example of SRF technology, as I mentioned already, LCLS2, so this is the example where the CW capability of SRF plays an absolutely critical role. So this is the 4GeV CW SCRF LINAC, and this showing the average brightness of the achieved and the X-ray beam for different photon energy, comparing LCLS, which was the previous machine based on the copper cavities, and then LCLS2, which is the current machine which has been built, almost all cryo modules have been built by now. So this is happening at SLAC, and then you can see, so this is European XFEL for comparison, which is also SRF machine, but a pulsed SRF machine. And then this is the LCLS2HE, which is coming along, which is double the energy of the LINAC with 20 additional cryo modules of SRF. So this is the, so what this CW capability allows, which will be demonstrated here, it's a very nice, actually video, as you will see. I don't remember who created it. I think it's someone from SLAC, but it's a very nice feature to demonstrate the concept. So this is essentially if you have a pulsed LINAC or pulsed machine, which you could realize also with the copper technology, likewise with SRF. So you essentially get snapshots of the busy street. Like this would be the images which you obtain of the system under study. So and then what happens? So by doing that, you are missing upon all the actually rich phenomena which is going on, which you can only reveal if you would have the CW machine. So this is a dramatic difference essentially between the CW capability of studies of phenomena using this X-ray light sources and the pulsed, which were enabled without SRF. Okay, so and then another one with the SRF, where the SRF technology plays. So this is not a collider yet. Again, this is, however, this is absolutely crucial application as well, which is the when the beam of protons is actually shot on target, in this case, to produce the beam of neutrinos. So this is actually the flagship Fermilab project, as you have heard. So this is to drive LBNF and Long Baselite neutrino facility and Dune experiment. And so this is enabled by the PIP2, which is a new CW SRF accelerator. And this is actually just a very fresh picture from yesterday, in fact. So when there was a groundbreaking of the cryogenic plant building for the PIP2 particle accelerator with, so this is Undersecretary Dabar, which was today at University of Chicago, as well Nigel and Leah Merminga and others. Actually, this is groundbreaking for the cryo plant. So this is underway, and it's also extremely important SRF accelerator. So now to the colliders. So I mentioned ILC already. So then there are at least 3 other major ones in consideration. So EIC, which is further along, so electron ion collider, which is happening at Brookhaven, so which is going to be actually a combination of 2 rings. So it's electron-ion collider, so it's going to be electron accelerator and ion accelerator combined. Then also the future circular collider, FCC at CERN, which would have several stages, or at least that's the plan which was discussed so far, of EE, EH, and eventually HH. Of course, there is also the circular electron-positron collider plan in China. So for at least the last two of these machines, so lots of CW power would be needed, so on the scale of tens of megawatts. So to handle the this light particles, electrons, positrons, synchrotron radiation losses, since this is circular machines. So an SRF, these are going to be also humongous SRF installations. So and for those, the quality factor will play a dramatic role as well, again, to affect the cryoplants required and so on. So and then that's somewhat different from ILC, for which the gradient plays, of course, a major role. However, as I've shown you, also the quality factor is the extremely important. So and then, so what's happening? Some of the very recent highlights. So this is the one very fresh. So there has been quite substantial progress in understanding also how to achieve these multi-cell structures at gradients in excess of the ILC specification in recent years. And this is just the plot showing some of these cavities actually going around the world. So it's Fermilab, Jefferson Lab, Daisy, and KK, where the demonstrations of these very high gradients, 45 plus megawatts per meter, have been performed. And so what's going on now at Fermilab? So given these advances, I'll dig a little bit further into the advances. So we're actually preparing the actual cryomodule demonstration at with the gradients now substantially higher what was achieved before or was considered during the 10 years ago for ILC specifications. So this is very exciting effort ongoing now. So this is kind of directly towards an ILC research. And then this is a slide from Zach Conway from Brookhaven. I received a few days ago on the ongoing effort for the electron-ion collider. So there are somewhat different issues which need to be addressed in addition to just performance itself of the quality factor and gradient. So there is also the need to mitigate high current. So you can see all these special power couplers, and you need the broadband high order mode absorbers and so on. So there is a broad program ongoing. So this is a practical aspect of implementing this SRF for a specific environment of EIC. So this is ongoing. So there is, and as you see, there's going to be 10 unique SRF systems over 6 separate accelerators: ERL coolers, synchrotron, storage rings, Krebin system, and Elena. Okay, so now a little bit further digging into the performance and how that eventually translates into enabling these colliders. So as many of you know, so performance of this cavity is essentially determined by the nanometer scale on the inner surface. So since they are superconducting, that's how far a few tenths of nanometers, how far the magnetic field penetrates into the wall. That's where all the currents flow. That's where all the dissipation happens. That's kind of almost all that matters. And then research into that and modifying that layer, that's the coupled with material science, that's the basic, that's the basis of the SRF endeavor in general. And then the other thing is you need a very advanced set of full-scale cavity characterization, clean rooms, and processing facilities, which are several places like Cornell and Fermilab and Jefferson Lab, and some others have to a less extent. So, but this is absolutely critical for performing this kind of advancement and development of SRF technology for future. Yeah, so that's mentioned here, and this is just a beam view inside the cavity, how these 9 cells look inside. So there is extreme attention to surface treatments and surface cleanliness as a part of the research. So, and this is another absolutely key part, which is key to progress, is actually the material science. So that has been the cornerstone, and understanding the structure of the tens of nanometers and directly relating it to the observed quality factors and gradients, that led to many advances. recent years. You can see that these are different techniques being applied to analyze the structure of this layer. This is just a bit on the same subject as I mentioned. So increase in Q that leads to decrease in required power for accelerators, and increase maximum EX rating, decrease in the accelerator length. And then, of course, this is another interesting domain which emerged in recent years. So what happens in very low fields? And we looked into that and understood the physics. So that actually enables quantum applications of the similar types of cavities. So I'll touch upon that in a little bit. So in this SRF technology in the last 5 or 10 years has been absolutely vibrant. So there was very large number of breakthrough, actually major, both understanding and performance. So, and this is just some of the highlights. So I will not go through them, but I'll, I just want to mention, so it kind of was a golden decade for SRF research in some sense. So both in implementing new techniques, such as, for example, nitrogen doping, which is the cornerstone of the LCLS2, CFC and LCLS2 HE, understanding low field Q slope, that's now the enabler for quantum. Large gradients, understood that it's, so the ones which I've shown, the combination of cold electropolishing plus slightly modified baking procedures and so on. But so this is just to visually show you. This was kind of a starting point, and that's so there were a bunch of previous performance limitations which have been understood and captured and conquered. And then, so what happened then? So this was the first of these breakthroughs, which is this nitrogen doping, dramatic increase in Q factor efficiency, decrease in cryo plant required capacity, some understanding that actually how you cool the cavities matters. This was also not known. So if you need to cool them in a specific way to make sure that the ambient magnetic field, whatever the remaining one after shielding is, actually is expelled. Then the nitrogen infusion. So this is the modification of this nitrogen doping with somewhat shorter affected, somewhat thinner affected layer on the surface, actually very thin, a few nanometers, which leads to the increased quality factor. So it's slightly increased gradient and, however, increased Q at higher gradient. So that's, as you've seen before, that's also required if you want to go to higher gradients for ILC or other colliders. And then, so finally, this is the very larger gradients achieved by the combination of cold electropolishing and modified 120C baking. So going forward, there is also there is several very promising leads in SRF. So about, I would say 15 years ago, so there was a discussion, is superconducting RF at the end of the road? It's very mature technology and so on. Have we understood everything is in path forward? So the last decade, I think, showed that actually it was absolutely not in the end of the road, but more like at the beginning of the road in some sense. So there was a dramatic number of breakthroughs. And so we are very optimistic and pursuing these leads to advance further. So some of these ambitious goals of what we are hoping for is actually, there are several ideas which may lead us even to the excess of 100 megawatts per meter, which is double the current, more than double the current gradients, and the quality factors also with the various techniques, doping and layering and so on, could go higher. So all of that, so all of this richness and kind of golden age, as Hassan Padamsi at some point put, of SRF. So what it's really acknowledged by this fact. So this is the map which I think Symposium generated of current and future machines planned around the world, either circular or linear, either for HEP, nuclear physics, or light sources. And you can see it's a very large number. And there is a substantial installations in existence and planned to be created around the world. Okay, so I'll just dig in slightly further into nitrogen infusion to just demonstrate to you this kind of method, which in general, so demonstrate the connection also to theoretical effort, which I think also part of the center of bright beams, but is also a very important part of SRF technology endeavor in general. So this was the 2017, the so-called nitrogen infusion advancement. So when it was understood that it's kind of inspired by doping, by nitrogen doping, so introduction of small amount of nitrogen, but in a very thin layer of a few tens of nanometers in the surface, which was also to be understood, but have been understood and shown that's what's happening, leads to this advancement in the quality factor, but factor of 2, which is substantial at ILC type gradients, and then also can advance the gradient. So since then, it just is highlights, so I didn't have time to put also other words, I just put some highlights which I had. So this is some of the work of Takayuki Kubo, which actually predicts, so if you have such a layer at the surface of a few, in this case, about 100 nanometers or a few hundred nanometers, sorry, a few tens of nanometers, as shown here, then it actually can lead to the, so theoretically, it can enhance the so-called superheating field, which is believed to be likely related to the gradient limitation in SRF cavities. So I will not go into details, but of course, if you're interested, you're welcome to contact me and we can discuss. But so this surface layer of this very few tens of nanometers of nitrogen apparently produces the second barrier, so-called, so there is one known Bean-Livingston barrier at the surface as well, itself, but then the existence of this inhomogeneity, so two different layers, introduces so-called second barrier, which further slows down the flux penetration, which is considered to be the gradient limiting mechanism at the moment. So this is so this fact that this layer of the impurities at the surface can be very beneficial. So it's being exploited actually further now. So, and it can be exploited in different ways. So it can be exploited either putting another material on the surface. So like in this case, for example, in the 13 on niobium, which promises here up to 120 megawatts per meter. Or you can have the diffused profile of impurity, as we have currently actually with doping, nitrogen infusion, and then more recently we realized actually with oxygen also. So it can be produced by thermal diffusion. So this currently at least up to 70 megawatts per meter, we believe the performance can be enhanced. And this is further analysis of this phenomena, which looking further into, so why is it so effect of this diffuse profile. The performance, this is by Jim South and others at Northwestern University, but within CBB, so Jim Stetna and others have looked at this, have looked at somewhat different structures, somewhat different distribution of impurity before, and but so this is the very important theoretical effort which comes along with the experimental exploration, and will further drive forward this technology. So, and then how to implement these new ideas. So what's happening, at least at Fermilab, and I'm pretty sure around the world elsewhere as well. So what we are gearing up to be able to actually create these special layers or special even further diffusion profiles on actual full-scale cavities. So this is the very large facility which will be able to handle all the 9 cell, 5 cell, and so on at Fermilab, which is to be commissioned in the coming months. So, and that would allow us to directly probe all these ideas which we develop, even to push gradients further and even further Q, are they realizable in the full scale cavity? And if they are, we are ready immediately to implement it in accelerators. Okay, so last few remarks on NB13. So this is another important development happening concurrently to niobium. I was talking mostly about niobium so far. So NB13 has not been implemented yet in an accelerator, but it has very substantial promise in 2 areas. So this is specifically for higher temperature operation, for example, at 4.4 Kelvin, which is due to higher critical temperature on NB13 itself. And then also theoretically, it promises the higher superheating field. Therefore, NB13 cavities in principle could be able to achieve higher gradients in the future. So they haven't yet, but there is a theoretical argument that they could. And so there was a very substantial progress in this area as well. So at Fermilab, at Cornell, and also Jefferson Lab. So specifically at Fermilab, so we had the first ever 9-cell NB13 cavity, so which has been actually quoted and demonstrated, and this achieved 15 megawatts per meter. This is a very, very important result for, again, NB13 and for multi-cell specifically. So you can note that it's 15 megawatts per meter, but with Q of 10 to 10 at 4.4 Kelvin, not at 2 Kelvin. So this already makes this technology certainly applicable to probably smaller scale industrial accelerators, maybe for FCC if it uses the lower gradient, and then also provides a good path forward for the future. So it's doable with the multi-cells as well. And this is Sam Posen, who I'm sure you all know. So he's the leader at Fermilab for this effort. And okay, so last couple of slides. So emerging non-accelerator applications of SRF. So what we realized over the last few years, that SRF cavities, because of the extreme high Qs, and because, as I mentioned, they are the highest efficient, the highest Q engineered resonators, they actually have applications, dramatic applications in QIS, in quantum information sciences, and also in as serving as particle physics detectors themselves. So this is for the QIS application. So we've taken these cavities, we understood what limits the Qs at now very low fields, not high fields as for accelerators. And by doing that, so and then we developed some novel treatment of how to achieve that, somewhat similar to accelerator type, but with some different flavor. And so we have outperformed the QIS state of the art substantially by a factor of a few hundred. There's a couple of publications on that. So, and that's actually currently serving as a foundation for our effort to work towards the realization of the, so what does it enable? So it could enable the realization of the 3D quantum computer, superconducting quantum computer with seconds of coherence. So, and why is it important? If you know about Google and so on and IBM, so the current state of the art in this field is of the order of a few tenths of microseconds. So, and again, this is promising seconds. So this is a huge, huge potential improvement, which we planning to realize in the coming years by partnering with Rigetti Computing and other industrial partners, where essentially one cavity here, one 9-cell 3.9 cavity coupled with one superconducting transmon, it's not shown here, but it's a very small chip. So 1 and 1, in fact, converts to 128 qubit quantum computer. So very exciting application of SRF coming. So, and then another one is actually by using this very high Q cavities, not an accelerator, but side by side in this case was in our vertical test stand, actually allows us to look for new physics. So in this case for dark photons. So this is so-called light shining through the wall type of experiment. One cavity energized and one cavity idle, but exactly synced in frequency. And then if these dark photons exist, so you will see the signal emerging in the empty cavity when you energize the upper cavity. So, and we actually have performed the experiment, and unfortunately we have not found the dark photon yet, but but we substantially moved the exclusion limit in the one of the energy ranges, or over the substantial energy range or mass range by several orders of magnitude actually. So this is just a couple last highlights. So, but to summarize, I believe these are exciting times for SRF technology. So we are eager to build colliders of the next generation. So we look forward, and actually we expect next breakthroughs in the years to come, as there are several very promising leads. And there will be, of course, a few enabling applications of SRF technology which are essentially boiling now. So this is very exciting time. And with that, thank you.
Thank you very much for the very nice talk. I think we have time for some question. Maybe I'll start with one question. when you try to push the accelerating gradient in a superconducting cavity, I think you mentioned maybe 120 or 150 ultimately. How does that depend on the frequency of the cavity? Because, you know, on the advanced accelerator field, people have the common belief that to go to high gradient, you need to go to high frequency.
So excellent question. So with high frequency, what so for the gradient itself, there is no clear dependence of the frequency. Why for the superheating field it would be worse, because it's DC superheating field concept to start with. But for the Q itself, so we know for same temperature, so the higher frequency of the cavity translates into lower Q just because the BCS losses are high. So the Q is going to be lower. However, that can be mitigated to a substantial extent with doping, for example. So because nitrogen doping, as we've shown, actually leads to the reversal of the Q dependence on the field. So at higher fields, the Q becomes higher. And this effect is stronger for higher frequencies. So for example, higher cavity with the twice as high frequency could have the same Q at high fields as the cavity with lower frequency because of this effect. So it's an excellent question, and higher frequencies could hold another advantage, which we actually explore in the formula. So higher frequencies means it's a shorter period. So, and if there are any processes happening on a time scale longer than this period of oscillation, for example, destruction of superconductivity in the walls, then this process can be suppressed. So higher frequencies could be better for high gradient in that respect. But so it's an open area of research. There is no clear-cut answer.
And the second comment, so all the cavity you guys are working with, they are the same elliptical shape, right? Or there is some work on optimizing the shapes?
No, so there is for I haven't shown that, but so for example, for PIP2, there are single spoke resonators, so SSR1, SSR2. But mostly for research, yes, we're working with elliptical shapes because they are simpler essentially, and all our processing infrastructure is best developed for that.
Okay, great. So are there any questions?
Philip, I have one question.
Okay.
Yeah, Alex, a fantastic talk. Thank you very much. For your the niobium 310 4.4 Kelvin Q value, the slope of that and niobium look quite substantially different. Do you understand? Yeah, this one.
Yeah, excellent question. So for NB13, so the problem which people are tackling now, by the way, this is a slide from Symposium. I forgot to put here the link, well, reference. But so this Q slope which you see, this is the main problem of NB13. And actually of films in general. So for niobium and copper films, even more so. But for NB13, so it was conquered to some extent at Cornell a few years ago. And there is not yet full understanding how to completely avoid the slope or how to make it 100% not there. But people now know how to make, or at least with some percentage, 50% of the time, how to make at least single cells without the slope. And so here you can see the slope in 9 cell, yes, which is stronger than in niobium. So if the origin of the slope is understood and mitigated, this would be also a big advancement for NB13.
Thank you.
Are there any other questions?
I had a quick question.
Mm-hmm.
I thought the light shining through walls idea was really ingenious, and wondered how it compares with laser-based experiments in terms of reach, or any other parameters you want to comment on.
Yeah, so for I'm aware of laser-based experiments which were performed, I think one maybe even at Fermilab a couple of decades ago. So in our plot, let me see, where was it? Yeah, so here we compare to, so the CROWS, that's another microwave based. Yeah, and CMB, it's so actually I don't have a clear answer for you on this right now, but it's an interesting question. I'm aware of other studies, but I thought so in principle, you can select any frequency. So the beauty of light shining through the wall is that you have known frequency of the source and known frequency of the receiver. I think for the microwaves, we have the super high Q cavities, which we can put on both sides. For optical regime, I'm not sure it was possible. So most likely for the optical regime based on that. So I think likely it should have been less sensitivity, but I don't have a precise scientific answer. So we have to, I can refer you to Ronnie Harnik, which is our theoretical brain on this. So, and he would probably give you a better answer.
No problem. I look forward to a dark SRF paper.
Sure.
Great. I think this concludes our session. So let's thank Alexander again, and also Gennady. Thank you very much for the very nice talks. And I guess that's it.
Right. So we can move to a panel session. Alex, could you stop sharing?
Right. I'm trying to, find where do I do that?
If you go
Yeah.
top, good. Let me.
Was hidden behind.
Okay. Okay, so okay, now I see it. Now we move to a panel session. We call it National Lab Panel, and we have 5 panel members: Sarah Cousineau from Oak Ridge National Lab, and Paul Gueye from Michigan State University, Michiko Minty, Brookhaven National Lab, Alex Romanenko from FNAL Lab, Gennady Stupakov from SLAC. So these are 5 the panel members. Since you already have instructions from 3, and I'll say briefly Sarah and Paul introduction. Sarah is the group leader for the Beam Science and Technology Group at the Spallation Neutron Source Accelerator at Oak Ridge National Laboratory, where she leads the effort for the production, measurement, and analysis of the world's highest power proton accelerator. She's also a joint faculty member at the University of Tennessee Department of Physics and Astronomy. Sarah holds a PhD in accelerator physics from Indiana University. She's highly engaged in accelerator community activities and is currently serving as the chair-elect of the APS Division of Physics of Beam and the curriculum committee chair for the U.S. Particle Accelerator School. Paul Gueye. Paul studied physics and chemistry and received both BS and MS in Senegal. He obtained his PhD in nuclear physics from the University of Clermont-Ferrand II in France in 1994. He joined the nuclear physics group of Hampton University as a postdoc in 1995 and participated in experiments conducted at Jefferson Lab and at the National Superconducting Cyclotron Lab and Facility. He was the chair of Hampton University's physics department from 2015 to 18. He is now a professor at Michigan State University, working at the National Superconducting Cyclotron Laboratory and the FRIP, Facility for Rare Isotope Beams. Paul has been and is actively engaged in numerous national and international committees pertaining to scientific research and STEM. In addition, Paul was recognized by President Barack Obama in 2005 for some of his work. So welcome all of you. And for panel discussion, we asked the CBB students to submit their questions in advance, so our panel members look at them and have answers prepared. So I'd like to first thank our CBB students for doing that. We had quite a few questions, so I grouped them into 6 categories. So one related to finding jobs at National Lab, and about research at National Labs, and mentorship, and promotion and career trajectory / development and job security. Another category, labs versus academia and lab culture. And then there are some other sort of category. So the format of this session will be that I ask the panelists to choose one of the questions group, and then they are going to answer that within a few minutes. Then the last question was any panelist can answer. Yes?
Before you go on, we can see only a corner of your slide.
Oh. Why is that?
I'm not sure.
Which corner do you see? Let me...
left-hand corner.
And we see Sarah and half of Paul.
We're not seeing the presentation mode. We're seeing the PowerPoint window with, you know, play from start and play from current slide, and so you probably need to select a different window.
Okay.
If you're displaying, you should select your. If you're in display mode, you should select your the screen that's being displayed, not the PowerPoint.
Yes, I'm using. Okay, let me. I stopped sharing, and what do you see now?
You're now not sharing. You're correct.
You're not sharing.
So share screen and then select the screen.
There you go.
Is this
now we've
okay?
got finding jobs at national labs.
Okay, is that okay?
Yes. Yes.
Okay. So okay. Okay. So now you saw these people photos, and then so as I said that the panelists will answer or address some of the questions relevant to each category within a few minutes. And then we'll go second half Q&A with the audience. So first, the set of questions about finding jobs at National Lab. I leave these two bullets there, and Michiko will address these questions.
Okay, so right, so I think I can assume that people are close to graduation and they're thinking about going to where to go work and are interested in going to national labs. So I would suggest that one starts early. So start by trying to get to know people in the field, either through conferences and or at the particle accelerator schools, and you know, not just attending, but by being very engaged, by paying close attention to detail, asking questions, just getting some face time out there, and hopefully finding common interests to talk about. When it comes time to interviewing, you know, all the national labs, they have websites where jobs are posted, so keep up to date with that. But I would also suggest that you talk to your advisor and ask him or her for contacts at the lab, so that you can both apply for open positions or just reach out directly and write a letter to introduce yourself and say that these are your qualifications and that you're interested, and ask if there are any opportunities and see if there's any resonance there. For the interview process, yes, there is, for a scientific position, you're often asked to make a presentation. So for the presentation, I would recommend that that you pay a lot of attention to the introduction. So sometimes the audience that will be present may not be intimately familiar with your work. So it's a big plus to be able to show that you can describe your quite complex research to a general audience. So the introduction is very important, as well as the usual things in a talk. But to open broadly is very important, so that you don't lose your audience right from the start. But that's common knowledge. But I think especially if you're coming in as a graduate student, where your topic is going to get very detailed, and again, maybe the audience isn't that familiar with your work. I think it's also important to avoid jargon, and make sure that you are cognizant of things that a lot of scientists feel are important, which are understanding of the basic principles, things that you might take for granted, even in definitions of coordinate systems, things like that. And it's okay to both during the presentation and in the one-on-one interviews that follow. I think it's something that I look for if I ask a question. I would rather somebody say they don't know as than try to answer a different question. So stay on topic, and I think it's okay to show what you don't know. In my view, knowing what you don't know is also it's not necessarily bad. It's a good thing, and if you're willing to communicate it, that's important as well. It's good to listen, and it's okay to ask questions. It's okay to indicate, again, maybe, it's not bad to ask a question back. If there's something that somebody's describing, just ask questions about it. Oftentimes, another thing is to interview or to apply broadly. So apply at lots of different laboratories. I think that the interview process is a little arduous. It typically involves traveling, preparing a talk, then one-on-one interviews. It can be a little exhausting, but it's a very unique time in which you often get to hear from the scientists who are telling you about the good things of the laboratory and working there. So you get a perspective of the laboratory that you rarely have a chance to see. And so it's often like the scientists are trying to sell the position to you. So it's really a valuable experience, and you only get that a few times in life. So the golden opportunity is when you first graduate. So if it is time consuming and a little exhausting, but it's well worth it. That further promotes the networking opportunities. You'll probably remember these people later when you see them. You get to hear about what the lab values, what kind of great science they're doing. And again, it's different from when you get hired and you first come on board. How much importance is placed on the publication record? It's always a bonus, of course. Teaching, I'd say most graduates have some teaching experience somewhere in their undergraduate or graduate careers. That kind of is part of it. It's a good exposure to something different. For outreach, that's not something that has been high on my list, but what I do look for is that, and often try to find out about, is whether or not people have kind of gone out of their comfort zones. So in a work environment, a topic comes up that needs to be done, or there's something out there that's not understood. It's not necessarily officially, a task that or part of the research line, but I like to hear about that. Something that caught somebody's interest, and they decided to kind of work or try to make a contribution in an area that's not necessarily in their comfort zone. That kind of goes along with what type of experiences make people stand out. And that's because at the National Labs, it is, much of the work that you're doing is very collaborative, as Yonki had asked about during my presentation.
Great.
One more very important point. In addition, if you're applying through the laboratory application process, make sure to include a cover letter. So it's not, the cover letter says a lot about you, that you want the position. That's your chance to put in unique details about yourself or your work experience. And I think that's a big plus. If it's a way to get noticed. If there's a huge stack of resumes, the cover letter is the way to get the first step out into the front.
Thank you very much, Michiko. It's a very good advice. So now let's move to research at National Labs. Gennady?
Yes, can you hear me?
Yes.
All right. So the first question, how difficult is to start one's own group in a national lab? And how does one go about doing this? Well, a quick answer would be very difficult. But having said that, I probably want to reinterpret this question. Probably the meaning is how you can, what can you do and go in order to sort of start working on your project, start to be noticeable in the lab. And there are many ways, and I can talk specifically about SLAC, that you can do it being a young researcher. We have what's called LDRD, and that's in other labs as well, which is Laboratory Directed Research and Development. And that's some money which every year director spends on the proposals in the lab. And there is a selection process, and young people write these proposals, and some of them get funded. And if you get the money, then you might work somebody with you, and it will be a small group. Or similar, there are DOE proposals. DOE from time to time announces that they want to spend money on particular research direction and ask for proposals. Again, young people write these proposals and can get funding. We have fellowship. At SLAC, we have Panofsky Fellowship, which is very competitive. And I believe at Fermilab, they have People Fellowship similar to that. And if you get it, then it's, I think it's 5 years or 4 years where you can do your research and your proposal. And then DOE has what's called early career rewards. That's a very good thing. And at SLAC, in the group Accelerator Research, I would say I know 5 or 6 young researchers who got it. The last one got it this year. And that's again for 5 years. I believe they give you 2.5 million to do the research. And that's, with this money, you can start forming your small group. And then there are, again, in the free electron lasers, which is close to me, there is Young Researcher Award. That's an international conference which gives this award. And if you are very good, at some point you can become a faculty, get a faculty position at Stanford University. It's like that. That's not often, but over the last 2 years, we got 2 young faculties. So there are many avenues, sort of get your group. You need to be active. You need to have good ideas and be persistent. So that's probably how I would answer this first question.
Yeah. By the way, Elena, you don't have to answer every questions because it's gonna take long, but you can just have overall answers because some of them are similar questions.
Right. So yeah, I'm probably talking also, there is a group promotion, career trajectory. What I was saying is relevant for the fourth group of questions. Are scientists, national labs less able to pursue their own research interests? Well, that's true. You have to recognize it. We are building big machines. We are building $1 billion free electron lasers or electron ion collider, and we have to be organized. And we are organized with the project, which does not mean that you are in a very narrow path. First of all, this huge project, they have different parts in it. And if it's a free electron laser, you can work on a gun or electron gun. You can work on a superconducting accelerator or undulator and similar electron ion collider. So yes, it's maybe somewhat limited, but then within the lab, you have a lot of opportunity. And finally, there is a third pretty large question. I'm not sure I can go in all the details. Maybe what I want to mention here that, let's see, what is, how often the emergencies of deadlines, you need to work extra hours. I would say I have a son who works in a startup, and compared work in a national lab, which what people do at startups, well, startups, you have much more extra hours, deadlines, and emergency. We are pretty relaxed here, but we also have some small deadlines. Maybe you need to finish your proposal, send an abstract, do something else, but I wouldn't consider that our job is such stressful. You need to take a on-call time. Well, if you are assigned to some shifts on machines, then that's probably true. I don't do that. I'm in doing theory. And I don't know how far I can go. Well, assignment, project, a piece of equipment, you take responsibility. That's probably true, especially if you go a postdoc. You are typically hired for some money which is dedicated for development something. Often postdocs come to SLAC and they are 50-50%. They are doing two different activities. That gives you some flexibility. But then if you are here, you start working with other people and you can switch to something else. So I will probably stop here.
Okay, that's great. Thank you so very much for the clear explanations and advice. Sarah will comment on mentorship.
Right, so I think that there's been a lot of increased focus on mentorship in the national labs in about the last 5 years, certainly more than when I arrived there, which is ancient history now. There's two types of mentorship, I would say. There's formal and informal. So let me talk first about the formal mentorship programs. Our national lab, and I believe all national labs, have a formal mentorship program. There's often a separate program that's designed specifically for postdocs, but even beyond that, there are programs you can sign up for, and so it's sort of it's by request, but a lot of people do it, and then you will be placed with a mentor who's in your sort of career path trajectory, but is not in your line of supervision. The idea is to give you that outside perspective. And you and your mentor will then discuss what you want to get out of the program, what the mentor can offer you out of the program, and then you'll set up regular meetings. Some people really get a lot out of those mentorship programs. Beyond the formal mentoring programs that national labs now have, there's also just sort of informal mentoring. So when you come to a national lab, you're going to be working in a big team environment. So you'll probably, unless you're a brand new postdoc, and even then there'll be graduate students below you, most of the people will be above you if you're a brand new postdoc. So you will find within that team of people those for which you have just sort of natural synergies in the way that you think, or you'll find someone that you really respect. And because mentorship is so stressed now in supervisors, in the national lab program, just about anybody is going to be willing to sort of adopt you as an informal mentor if you just show up in their office and start asking questions. I think national labs are very supportive team environments. I personally have had both successful informal and successful formal mentoring throughout my career. So I've done both at different times. And then what you'll find is as your career trajectory progresses, you will have mentors for certain areas of your career, certain people you rely on for this subject, or certain people you rely on for that aspect of your career, and it will sort of evolve. Naturally, you will begin to mentor other people. So as you spend more time at the lab and you move up the ladder, you will have people underneath you, and you will begin to mentor them. It is part of the expectation at national labs now, and it's because people are actually evaluated on this in their performance rating, they spend a lot of time doing it. So I think the mentorship programs at labs are very strong, and they're becoming stronger all the time.
Great, thank you, Sarah. It's related, but this next question is about promotion or career development and job security. Alex?
Yeah, thank you. So I'll start with job security, which I think is an important question. So the short answer to this question is it's very secure. So if you compare all possibilities which typical graduate faces, it's university or academia, industry or national labs. So I think industry in that sense probably the least secure, because it's a very dynamic environment. There is very frequently you can hear layoffs here and there. So national labs are certainly not like that. So and in addition, so national labs, so most positions at national labs actually, except for scientific positions, which starts for postdoc, I'll cover that a little bit, but most other positions are actually permanent. So technicians, engineers, they all hold, most of them actually, permanent positions. And those I would rank as probably the most secure positions, around. Because you can compare at universities, there is professors, tenured professors. So those are really secure as well. But the rest of the staff is not in that status. So, and then at national labs, so if you're considering, for example, engineering or other types of positions. Those are very, very secure. So scientific requires somewhat longer path. However, eventually when you reach the permanent staff position as a scientist, it's also extremely secure. So we like to compare it, and Yonki on both sides, so you can also add to that. So, but we like to compare our permanent scientist position to tenured positions at the university. At Fermilab, for example, there was even a correspondence between the kind of established, that was one of the ideas. So associate scientist, which corresponds to roughly to assistant professor at the university, which is tenure track. So assistant scientist, associate scientist, typically is something which comes after the postdoc, and which a person, if he or she gets that position, holds for, it's usually 3+2 or 3+3, or depending on the, so at least on the scale of 5 years, after which it could be earlier also depending on the results, which is also a substantial difference from, I think, most universities. But then you are reviewed for the achieving this pseudo tenure track when you're converted to permanent staff scientist status. And in that, it's very secure as well. But so on the career trajectory, so usually the entry level, if you're just a fresh graduate of PhD, let's say in science, and you want to pursue scientific track, that postdoc usually first step. And it's very important, as I think Michiko and maybe Gennady also touched upon, it's very important when you join a postdoc at the national lab. So very important part which you gain is you actually get to know both people and efforts around. And then frequently what happens with postdocs at national labs, so unlike at university, it's sort of almost an expectation. You complete your postdoc and then you look elsewhere for the potential academic positions. But at national lab, frequently postdocs get converted to permanent positions. So at least they know which positions could be very suitable for them to apply. So it's very, very very common, substantial percentage of very good postdocs who actually performed well, at least in the accelerated technology area, that we, at least Fermilab and other national labs, try to keep them and try to perhaps offer them permanent positions. So that's a very important part. But for scientific tracks, so postdoc and then associate scientist, or one of these fellowships, as Gennady mentioned, so People's Fellowship or Wilson Fellowship for example, high energy physics itself. And then, so that's how you progress. So, and then typically after you are in the, so it's almost unheard of. I think there could have been a couple of single cases in the history, at least of Fermilab, when scientists had to be laid off at some very dire times. Again, Yonki, you may you may comment on that. I think there was maybe 2008 crisis when maybe 2 scientists or something was, but it's really unheard of. So scientist is very equivalent to tenure track, I would say. So if you, to tenured position at the university. And that's backed up, if you want, by the government endowment. So these are government ran labs. So in government, it's almost infinite endowment in some sense. And universities, there are some of them private, but it's more standalone entity. So there is some job security coming from being also government associated. Okay, so and then how is success measured? So someone mentioned also publications. That's important, but not as important as academia. So I think what success mostly is measured by the success of the group which you're part of. It could be smaller group, larger group, and your contribution to the specific task. Because the tasks at National Lab, the National Labs have missions. So it's, for example, Fermilab has very specific missions. Some other labs are more multidisciplinary, but they usually, so it's not do whatever you want. It's specific missions, and it's kind of measured based on your contribution to the subset of that mission. And that's evaluated by your circle of supervisor and so on. So, so what does your boss look at when it comes to promotion? That's what usually the bosses look at. How successful you were in, yes, doing research, but doing research as a part of the larger mission, if you will. So, and for the opportunities, continuing education, professional development, so all of those are present in abundance. For example, for technicians, so there are certain cases of technicians who want to progress to engineers. So they are very talented technicians, have very good skills. So there are opportunities when Fermilab pays for the education at the university. But for scientific workforce, there are some examples. For example, there is, if people aspire and show promise in leading projects, for example, or want to take a prominent role in projects. So then there is, for example, the strategic leadership, strategic lab leadership program, SLP, which is ran by Chicago with other labs, where people actually go to business school. So it's run by business school out of Chicago, and they get this special education. So it's a plenty. And for the conferences, workshops, I think, at least in SRF and other areas which I witnessed in my roles. So national lab delegations to major conferences on the fields are usually the largest by far. So they are larger than any specific university. So it's very, so there is no usually, there is no problem to visit the or attend the conference if you have, again, if you're involved in something which you are presenting or you're part of a larger team. So it's usually very, very easy. So I think that's my.
Great. Thank you, Alex.
Yankee, can I add a few words to the subject?
Sure. Would you be a bit brief, or we can come back? But if you want to have a short comment, please go ahead. Yes.
Yeah, a short comment. Alex was talking about safety and layoffs, and I would like to add that I've been at SLAC for 25 years now, and I did see some layoffs over this time. When people have to understand that we are funded every year by Congress, and the funding can go up and down. But what I saw, usually people who are asked to leave the lab, they somehow lose contact with the main direction of what's being done in the lab. So when you come in the lab, you want to make sure that you do not become disconnected from what people are doing around, what's the main goal. Then there is the danger that at some point you will be asked to find another place for work.
And I think
understanding mission is important.
Yeah, mission. To echo what Gennady said, yeah, we don't, actually, national labs, I don't think they want just individual researchers to come in and get their own grants, get their subgroup. They want to bring best people to contribute to mission eventually. So that's a fundamental difference with the university.
Okay, Paul, we have more questions here, but Paul will address labs versus academia with his experience, both locations and also lab culture.
Okay, that was a lot of questions. So
yeah, you don't have to have Q&A, all that, but just some general answers addressing most of them.
So let me put first put that in perspective for, I guess, for students. Think about it as well, there's two pieces. One is think about it as a family versus work environment. So when you grow up, you're basically defined by where you, of course, which family you have and your environment, which school you go to. And this shape more or less what you're going to become before you start in your work environment. But the family also have some particular features because you can be completely open, you can share a lot of information, you trust people around. So there's a lot of qualities and sometimes not so good, but it's part of growing up in a family. In the work environment, you have colleagues, and whether you need to learn how to work with people, whoever they are, and you may or may not like some people, but they may be the best person in their field, and you will have to work with them to be able to achieve the goal that you want to achieve based on the mission that was just mentioned earlier. So keep that in mind because that will define, that will basically drive more or less what I'm going to mention later. So in academia, typically you work with an advisor, you're in a particular research group, and you have access to some resource and performing very well, everything is fine. The difference within a national lab is that you basically have access pretty much to the entire lab. Now, that doesn't mean at university people don't do that, but the lab being, well, it depends on which lab you go to, but you do have the ability to work with pretty much the best of the best in this field. and you can reach out to them at any time, any moment, which means you can really build a lot of skills that you would not have been able to do it at a university. Also, the process in academia sometimes are pretty lengthy in regards to paperwork when you want to get things done. I don't have hair, so I don't have to pull them like other people, but sometimes going through a lot of issues that do not make sense with the administration is a big headache that you don't usually find at National Lab. Now, you are sometimes also more, there's more relaxed in regards to what you can do in academia. People are not going to fault you because you're a student, and if you're a faculty, you're also part of a system that sometimes it's, as I say, it's not easy to navigate. But at the National Lab, you do have to deliver on particular products. So that's another key component. In regards to the culture, so I'm probably not the best person to answer that one, but I'm going to answer it this way. Everybody is different. Some of you are more proactive than others, but you can make the environment what you want, whether the culture is something you're comfortable or not. I'm going to give just a very simple example from my own experience. I'm originally from Africa, and as the saying said, it takes a village to raise a child. And when I started at JLab, everybody in front of their computers to get the first experiment on the floor. I mean, we have to do it, so everybody focus on that, but I don't like that. I like people to interact. I like the human interactions. So I started reaching out to people, shaking hands, hugging, and next thing you know, we were having fun in the counting house. So you can make changes depending on who you are, so that people will benefit from your contribution as well as you benefit from others. So it's demanding, sometimes it's frustrating, sometimes it's scary, but it's up to you to, you can actually adapt and change that to your advantage so that you can be successful. And I check with my team all the time from midnight to midnight. During holidays, I mean, we basically becoming a family as well. So this is something that is important to me, but it's important to any human. You cannot live on an isolated island, right? So the more you can build connection outside of the lab, the better, because it helps you also to be more aggressive if you need something. The person that knows the answer may be in the next office, and if you don't break the glass, I mean, you're going to get stuck for too long and eventually fail in whatever you need to do. So I think I'm going to stop here because I don't want, sorry, mid-20s. So areas. So you're, the good news is that you're all physicists, which means usually we don't party much. We tend to socialize with our peers, but so it's a little bit hard to answer on that one. But again, you can make things happen. Nobody prevents you to have to invite some colleagues at your place, or to go to some colleagues' place and have small parties if that's something you want to do. It's not, of course, a big city if you live in a remote area, but you can make a lot of fun. And regardless, you're gonna be so excited about what you do that sometimes you even lose track of time. So,
great. Thank you, Paul. Okay, there are a few other the questions. Maybe any of you can take one of these questions. So first one is, what is one thing you wish you knew about working in a national lab before you started? I think that's a very good question. Anybody?
Yep, I can start.
Okay.
I wish I knew nothing. Like I like I did when I came from France, because I'm also an adventurist, and for me, it was basically, whoa, that's great. Let's learn everything I can learn, and just swallow everything you can swallow. You're going through a discipline that is pretty demanding in some ways. So I don't think none of you will have any issues adapting. But getting into a national lab is it's like walking into the Alibaba cavern. There's so much stuff, and it doesn't matter how much you know. Be sure, of course, that you're good at what you do. But you can basically contribute and expand your knowledge. If I knew already what I was going into, for me, it would have removed all of my creativity, because I ended up being in the place JLab and FRID now, where there were these were completely new environment for me. I haven't been in the US, and the way the US worked, the way those labs were working, JLab I was there when the first beam was came out in Hall C, and we had to develop everything from scratch, which was fantastic. I learned a lot. And at FRID, I'm an electron guy by training, and I'm now working with heavy ion. That's fantastic, right? So based on your skill and your experience, not knowing sometimes is good, because you can actually contribute significantly to the scientific program based on your own experience and skills.
Thank you. So second question, how much are you impacted by government shutdowns and changes in funding at the federal level?
I can take that one.
Sure.
So I've watched that happen on and off throughout the years, and I can tell you at least that for me, the answer is very little. So obviously changes in federal funding can slow things down or speed things up, but I haven't seen a mission scope change or any big changes in my job due to the annual budgets at the federal level. So sometimes we hire a little more one year, sometimes we hire a little less, but what my job looks like year to year seems to look about the same.
Mm-hmm. Great, thank you. What's the most interesting thing you've gotten to work on since you started?
Maybe I can say a few words.
Okay, Gennady.
Most interesting, usually when you start working on something, it's most interesting, and then you work it out to the end, and then becomes boring, so you move to the something else. Maybe I would slightly modify this question, and I would say that when you start working on something and it's a difficult problem, you have to be persistent. And in my scientific life, I had this kind of moment when I've been working on an idea. I had an idea a long time ago, and I wanted to apply it to the free electron lasers. And I was trying to do this probably more than 10 years, talking to different people and trying to address this in different ways, until I came up with a solution which eventually brought me this FEL prize that Philippe mentioned in my bio. So it's not so much interest. You should be interested, but what's more important, I think you have to be persistent.
Mm-hmm. Great. If you could change one thing about your current job, what would that be?
I'll take another slab at it, but it's going to be almost the same as the first one. So I just mentioned, well, let me put it this way. I'm going to rephrase that also. Right now, most of you are, you're in this particular workshop. That means you're doing accelerated physics or something related to it. And you ended up at this particular point in time, sometimes because that's where you wanted, sometimes it's just how nature directed you to be where you are. So for me, it's the same, is you're gonna get some training, some skills, and very often life will guide you into a particular area. And I would not change it because whatever you, all the skills you have acquired are unique compared to another path. And this makes you unique also on how you can contribute to whatever you're gonna end up.
Great, thank you. Thank you all for wonderful answers and advice. And I think this is a tremendous, and I think we covered pretty much all the questions and people wanted to know more about national labs. So this is a tremendous. Now we have about 15 more minutes, and anyone who has questions?
I guess we answered everything that they had in mind.
Okay, while we are waiting for other questions, if each of you pick one set of questions, but if you would like to add some other questions, that's totally fine too. So any further comments or answers, it's welcome.
I can comment on interview, how I do it, what the most important for me.
Sure.
When I do an interview, I like to go through the publication list and looked into the papers, and then to start a conversation maybe on one of the papers which I think is closer to my understanding, and to go from there. And I actually had an interesting story. Now it's more than 10 years ago when an applicant, the Chinese fellow, came for a postdoc position, and I looked at his papers, and I found that one of the papers is completely wrong. So we had a very lively discussion with him and tried to convince him. And then he got an offer. And it turned out that he was an extremely bright person. I spent like 10 years working closely with him, and he got his early reward, FEL early reward as well. Now he came back to China. He has a full professorship there and a very nice laboratory, and publishes PRL papers often. So it was interesting development of that interview.
Yeah. I think it's a kind of you have to know the audience, right? So also most of your comments and advice, it's not just applying to national labs, but it's academia or industry, any we're talking about not only interview parts, but also working and creating environment, culture. Of course, you like to go to a place where it's a good environment, but you also can contribute. So I think that kind of mentality, a lot of things, not just the national labs, but apply to anywhere you go.
I have one thing to add to the job interview process. That's something that we do that probably everybody else does too. Mm-hmm. And just something you should expect is that we look for the informal reference. So obviously your job application comes with people you name as formal references, but it's really important that you're visible as a graduate student to a lot of people in whatever institution you're in, because we know people there and they may not be your references. But one of the first things we do when we pick up when we receive an application is we pick up the phone and start calling people who aren't on the reference list. So it's good to be engaged. Make sure that people know who you are, advertise your work, and work hard. That was my advisor's motto: work hard, make an impression on people, because those phone calls do happen behind the scenes.
Yeah, absolutely. Yeah, that's true also to all the institutions. So
yeah.
So Yunki, I'll add one more thing also on the question. Are scientists in national labs less able to pursue their own research interests? I think the kind of correct answer, so in some areas they may be more able to pursue their own research interests, because, for example, if research interests, just to give a couple examples, if you are interested in building accelerators, then it's that's national labs is almost a unique place to pursue that, because it's just the scale of the things which are being realized and being part of that group and working on those research problems. So yes, in some areas, if it's like some individual narrow areas, it may be harder to pursue a national lab. But if your research interests are aligned with some of the things, of the larger scale, it actually may be more able to pursue, maybe actually the only place to pursue. So just to keep in mind. So it's not one more restrictive than the other, it's just different kinds of problems being addressed.
Yeah, I agree with that. There's a general mission at a national lab, but if you come up with an idea that supports that mission and it's your own idea and your own direction, that would normally get adopted by the lab. It just needs to be within the regime of the mission.
Exactly.
It needs to contribute.
Right. Any other comments or questions?
Yeah, I'm going to make a general comment just for all the students. I mentioned that also to my undergrads. When you get into a panel or you go to a seminar or whatnot, it's always good to ask a question. Young Kim asked who wants to ask a question because of a simple thing, right? I mean, whoever's going to ask a question, we're going to remember too often, oh, that was that student who asked that question. So now you're becoming, you're basically raising above the average students just because you ask. So if you know who the person who is coming on the panel or giving a seminar, do some quick homework and just ask one question, especially if that is a person or lab you want to get into, or a person doing some research that you're interested in. If you're quiet, you basically disappear into the cracks.
Right.
So ask, and we always say no question is stupid. Or if you don't want to ask your question, be sure to follow up after the seminar or the panel or whatnot, and shoot an email to one person that you found you want to follow up with. But you need to be proactive.
Yeah, I mean, that goes with also what Sarah's comments, right? Because there will be, people will check on you, even if you didn't write letters, because you want to know whether these people in their environment or, how good they are. So I think it's all be connected. Any other comments from panelists or any new questions?
There's a question in the chat.
Question in the chat. Here. What upward mobility is possible after being hired as a staff scientist?
It depends if you want to sleep.
So this is a promotion we are talking about, is that right?
It looks like it.
Mm-hmm. Yeah.
Yeah, I'll give a very short answer from my end. I mean, it depends. As I say, it depends on if you want to sleep, because I mean, coming up with great ideas is great, but too often that also means you own it, and after it goes up. Now, the higher you go, the less research you do, because it becomes more of an admin at some point. So it really depends on how far you want to go, but the sky is the limit.
So I'll add to that also. So, I mean, national labs, they have somewhat different gradations. They're not exactly the same at all the labs. But so staff scientist, so it usually actually several levels. So you start, the first permanent level is, the FNAL, let's say it's called scientist. Then the next level is senior scientist, which is usually terminal destination. And then some small percentage of scientists who are really doing substantial advances in the respective areas, they can get promoted to distinguished scientists. And another upward path, if you will, is also, as I think Paul mentioned, and also could be administrative and also the project leadership. So many scientists assume the roles of leading the specific project, like leading construction and commissioning, let's say, of specific project at FNAL. So that's another upward, if you will, progression. So there are several routes which exist.
Mm-hmm.
They can be both also. Some people do both. So they both excel in, science and assume leadership roles. So, yeah.
There's another chat.
Oh,
no.
No, it said thank you. I got it. Well, looks like we covered all the questions and concerns from CBB members, and I'd like to thank our panelists once more. Let's give them a big round of applause. All the wisdom and you know, this comments and advice, and I think this is fantastic. Again, as I you know, most of the answers are relevant to all type of positions, so it's not just a national lab. So this, in that sense, even your comments apply to many of us in general. So with that, I think we are ending our symposium, and we had a wonderful speakers, panelists. That's fantastic. So Ritchie, as a director of CVB, you want to make a final remarks?
My main remark is just thank you to everybody for coming and making a really splendid, very interesting day for all of us in CBB. Really appreciate it. And thanks to all the students and postdocs who presented your work in the poster session.
Right. And, okay. Yeah, go ahead.
No, that's it. Thank you, Minty, for organizing.
All right, so we are a few minutes ahead of schedule, but nothing wrong with that. We've done. So thank you again, and have a, well, we cannot say have a safe trip back. Now we are all at home. That's the beauty of a Zoom. Okay, have a great evening, and see you next year annual meeting and symposium. Of course, we will see each other more often, but symposium and annual meeting, we will have another one year from now.
Thank you, Yankee.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you.